I'll try to finish by 45 minutes, maximum 50 minutes. That's my hope.
Yeah, that's fine.
Okay. And open it up for questions, of course.
Yes.
And would it be possible for me to listen to the other lectures as well? How is that link done?
Yes. In the same link, you could be a part of that and you could listen it.
Right. Okay.
But yours is the last keynote
for today.
Keynote address for today.
Okay.
Tomorrow we do have 3 keynote speeches. Maybe you can also join for that.
Yeah, I'll try. Yeah, I don't know. I just wanted to know how. And about the paper presentations, how is that done? Also through Zoom?
That's also being done online.
Okay.
So some of these, sometimes research scholars, student, faculty,
right,
they do present the papers.
And was it only open for VIT students, or is it also open for
No,
other
no. It's open for all.
All right.
But this has been done within a short notice of around 1 month or so. So
yeah, I understand. Yeah.
We usually get a huge amount of paper, but since the time is very less, somewhere around we have screened 26 papers for presentation.
It's still a good number for
good,
2 days.
Yes.
Yeah, and doing it online is also making things a little tough, right? It's not.
Yes.
It's not the same as talking continuously on a stage.
But we are now getting acquainted with this because all our classes becomes online.
Right.
So now we are used to it. So how is the weather there?
Yeah, it's okay. It's kind of summer, kind of.
Okay.
Yeah, 22 degrees maximum. That's all.
Oh.
Yeah, it's mostly always cold.
Okay.
There's somebody sending a chat.
Yeah. I was just
right,
greeting all participants.
Got it. Yeah. Okay.
So as per my system, it is 3 more minutes are there.
Yeah. We'll wait. It's okay.
Start exactly by 2 o'clock. So for some time, you have been associated with some of the universities regarding some of the researchers in EMC, right?
Yeah. Even now, I'm involved in. I teach in a few universities in France.
Oh.
I run about two, three courses for them even now.
On EMCs?
Or on EMC, automotive electronics.
Okay.
Yeah, on those topics, and microcontroller.
Oh, fine.
Right. Programming. Yeah, certain things like that. I've been doing it for the last now 10 years.
Oh, great.
Yeah, almost. Yeah.
So how about collaborating with VIT? I was just thinking of No, asking.
Always open. Like, but the thing is, I don't think there was any subject specifically looking for EMC as a module, or you know.
Yeah, yeah, that's true. Not specifically, we didn't keep a separate subject on EMC, but
Yeah,
MTech
yeah,
PLSA subject. Uh,
yeah. Something in automotive electronics. Yeah,
yeah,
it
they
can.
come across signal integrity, like couple
Okay,
of chapters on signal integrity issues.
right. Yeah, so my expertise has been around microwave engineering in microelectronics, then RF design, EMC. So mostly my association with universities are still going on, helping a few PhD students around in this
Oh,
field. Yeah, but otherwise, look, 95% of the time I'm in the industry, so it's tough to find time to go around the universities and keep teaching.
true,
So
true.
France I did because I did my PhD there, so I kind of continued
Yeah, yeah,
working with
yeah.
them.
Good. Jagan, can we start?
But the participants are only 28, sir. Can we wait for 1 or 2 minutes?
Yeah, we'll start for a couple of minutes and then start.
In a couple of minutes, we'll start, sir.
Yeah. Actually, post-lunch session is a bit challenging session. But I believe Abhishek will take care of that.
I hope. Yeah, for me it's still not 9:30 in
Yeah,
the morning.
yeah. For you, it's somewhere around 9.
Yeah, 9:30. Yeah.
So.
So this is the first conference on this topic, is it? IETCCSD?
Yes, yes. So after this COVID, we thought of making some of the conferences in virtual. In that context, from our department, this is the first conference going online
Yeah.
completely.
And have you done similar conferences on circuit and system design?
No, 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 no.
Okay.
So this is the first conference on the same topic.
Right.
Maybe it could be extended. Let's see.
Yeah, it depends. Yeah, of course. If there's a lot of interest,
Different version of that.
Exactly.
So being the first year, I think like after the COVID period, we plan to have this. So strictly speaking, we conceived this idea sometime in July, starting of July. Then we started working towards that.
Okay. So I see even Shivanandam sir is also very active.
Yes, yes, yes. He is in fact involved in that ITC testing all this.
Okay.
Just last week back, he was also one of the co-organizers in that ITC conference.
Right. Yeah, he was the one who taught me VLSI many years ago.
Can we start, sir? I think.
Yeah, Shivan. Yes, Jagan. We may start. Let me just welcome, and then probably Jagan, you can take it forward. Good afternoon, participant. On behalf of VIT and IETCCSD conference team, we welcome you back for this post-noon session. So as I said in the morning, this session will be concentrating on EMC. Really, this is the need of the hour, particularly those people who work on IC design and things like problems with the EMC problems. Uh, we have the right person to address all this. In fact, he has been working on this for around 10 years, and he is also an alumni of VIT. So now I call upon Professor Jagannathan Naidu to give a brief introduction about Dr. Abhishek Ramanujan.
Thank you, sir. I am honored to introduce Dr. Abhishek Ramanujan. Dr. Abhishek joined Analog Devices, Ireland in 2015 as a senior systems consultant and mentor, following 8+ years of EMC research, modeling, design, and development in automotive electronics. He is an alumni of VIT, 2007 Telecommunication Engineering batch, gold medalist. He received his master's and PhD degrees in electromagnetic compatibility from the University of Rouen, France in 2011. From 2011 to 2015, he was an EMC expert engineer at the Valeo Group, France, where he was actively involved in design for EMC aspects for automotive electronics. In this current role, as an automotive EMC system engineering lead at Unlock Devices, his focus is on spreading EMC knowledge on application and systems across ADI with the objective of driving solutions with the high EMC performance. He is a recipient of the prestigious IEC 1908 award for exceptional contribution to the IEC standards group. Thank you for accepting our invitation. Over to Dr. Abhishek.
Thank you, Mr. Jagannathan Naidu, and thank you, Mr. Shaktivel, for giving me this opportunity to, in fact, share my experiences and maybe thoughts for future in the evolution of EMC, which is electromagnetic compatibility on IC and system design. And I hope all of you have been having a good conference today and expecting you to have a good conference tomorrow as well. So moving on to the talk. So as your professor said, it's mostly related to EMC, right? And how IC and system design are closely mapped, right? Sometimes not everything is so straightforward. I'll talk through those things. Right, so this will be the outline for today. All right, so I'll start the introduction to the electromagnetic compatibility term, right, with some real world examples. And then we will move on to the core subjects, which is role of the IC in system EMC design. And this term is important, the term system EMC, because a lot of EMC is, I'd say, legally important at a system level, but not at IC. So you will see all those things in this part of the talk. Then we will look at some close, I'd say, items at ICs that contribute to emissions. So I think as VLSI engineers, as microelectronics engineers, as designers, you'll see what are all the things that could affect emissions. And the same thing holds true on the susceptibility or the immunity side of the IC design. Right, so by the time we get in here, I think there will be, I'll try to explain what this emissions and what susceptibility is, right? So we'll get to the point. And of course, we will talk about the people available in this field and the tools that are available. And finally, I'll conclude the presentation, right? Now, although these are all my favorite topics, right, I am not going to talk about electromagnetic theory, no Maxwell's equations, no antenna theories, and no microengineering, okay? I'm not going to bore you with all equation stuff, nothing. It's going to be very practical oriented experiences. Right, so one of an important, I'd say, published information, right? So this is an example of an EMI issue in a medical device. So this, you can go to this link, right? It's available. You can go read through this. So there have been some people studying, trying to study some EMC on devices that are in the market. They're all compatible. They're all legally sold in the market. They're all tested for EMC as such. Now, this is the defibrillator and, I'd say, portable suction devices. You could have a situation where the systems can be completely inoperable in a medical emergency due to an EMI event, right? So these are examples, again, published in this link. This Philips HeartStart MRX defibrillators are known to fail without a warning, right? If when subjected to a very high EMI, and the other device, LS4000, you could see, failures happening at about 180 volts per meter. Now, 180 volts per meter is realistically a very, very, very high value. Okay, it's not common to find this in the environment. Nevertheless, you may be in a situation where you could find, such field levels, and this equipment in those environments could fail, right? So this is a practical problem. It may not work as expected. Okay. Now, more close to me, right? A lot more in automotive, where I spend a lot of my time on. Now, these are all problems. Again, I just mentioned these are all problems that have been published. A lot could be there that are not fully understood, right? So some of the recalls in automotive were related and are related to EMC and EMI issues. So 2010, there was a famous sticking pedal problem. Okay, I won't name the car maker. It's up to you to go and read, right? So there have been instances where you'll have a sudden unintended acceleration. Okay, and it's something to do with EMI. It could be anything else. It could be a software problem. It could be so many things, right? And the problem here was, of course, the guys had to do a lot of analysis and find out that, you know, it was indeed related a part to EMI, and EMI generally leaves no trace after the incident. So it's very difficult to go back and go to diagnostics and see if it was an EMI problem. Okay, so it's almost impossible. And finally, EMI can also confuse the software. So for example, instead of giving an expected value, it can create an unexpected value that the software thinks something is going wrong, right? So like EMI has been a problem here. Similarly, in 2013, there was another car maker who recalled more than 1 million cars because of an airbag problem, which could accidentally deploy without warning, related to a lot of filtering problem, right? The filter got damaged, burnt out. Some components got burnt out during, you know, over time. So these are all, as I said, published, right? There could be a lot more. And similarly, I'm just showing you something, the image that is shown below here. This is dating back to 2002, right? So this is an article published so many years ago. And this was an interesting use case because a car was sold in the market, right? And some, I'd say, curious engineer who bought the car started measuring the magnetic fields inside the car. Now, don't ask me why he did it. It was just his curiosity, probably. So when he measured the fields, the magnetic fields inside the car, at different zones, you can see the red, the black, blue, the orange. He could find, the engineer found out that there are some locations, mainly near the front panel, where you have the climatic control, you know, all the air conditioning unit, the fan blower, whatnot. At that location, the magnetic field, now represented here in microtesla, it was the maximum, right? And as you go some sections of the car to the front left, back left, the fields were much lower. Now, there's nothing wrong in it. Okay, it's quite normal for things to happen, but the big question mark started kicking off a big question. Say, okay, guys, this is normal car. This is a classic car with classic devices. If we see such high magnetic fields, what would be the situation if we were, you know, go ahead and do electric hybrid cars, which are quite common today? How do we get this magnetic field under control? What is the so-called safety, as long as it's safe for human beings to sit in the car and drive in the car? So this kicked off this topic in 2002. And since then, there has been a great progress in this field, right? Like there are standards for this now to say that when you make electric cars on any car, in the low frequencies, mainly in the 5 kilohertz, 32 kilohertz frequency bands, which is typically the electric car, say today's switching frequencies. Yeah, it is important that the magnetic fields don't exceed a certain value, so that it is safe for human beings. And there's a whole medical thing associated with this, right? About safety for human beings with magnetic fields, right? So this is dating back 2002. So the reason why I get this example is if you see the examples here, 2010, 2013, 2002, right? That have been consistent problems in EMC, right? And it is only going to be a bigger problem as we proceed. So what is this EMC, right? So EMC is nothing but electromagnetic compatibility. Okay, that word compatibility is very important. It refers to the ability of the electronic and electrical equipments to satisfactorily function in an environment without disturbing that environment. So meaning it should satisfy 3 criteria, right? 1, it should not cause interference with other systems. Okay, it should not be susceptible to emissions from other systems. And finally, it should not interfere with itself, right? So this is all about the compatibility term, and it means it's a balance, right? We should not disturb others and don't get disturbed by others, right? So this, it's easily said than done, right? A lot of this goes through experience, a lot of this goes through design, and I will talk through those items. Then this brings another big topic of EMC being a legal item. So you might have seen as you buy any electronic item in the world today, right, at least in the last 10, 15 years, you will see some logo, the CE, which is on the right here, okay, something like this, or an FCC logo, or sometimes both, okay. Any phone, any mobile phone, for example, any laptop, right, any refrigerators, any equipment that we buy, right, any electronic equipment. So CE, that whatever, CE or FCC, right, it's used, the mark is used to state that that product, okay, is kind of safe to use in the environment, which means it has gone through some level of EMC testing, right? It depends. That level depends between classes, right? You can have residential parts, you can have industrial parts, you could have automotive parts. So that's a different topic altogether. But whatever it is, there is a CE committee, that is the European conformity mark, and you have an equivalent in the US, right, for the FCC, right, which is certifying for electromagnetic interference from the device, and those should be under limits. Now, if you go by numbers, technically both CE and FCC are very commonly used. They are very similar, and CE marking on a product ensures free movement across the European Union single market. So that's very, very important. If somebody makes a product, say in some country in the world, and they want to sell it in Europe, that has to be a CE mark, right? If it's electronic, it has to be. So they are recognized worldwide, right? And some countries may have their own certification procedures and limits, right? And by definition here, what is this product? So the product is actually the end product. As I said, it's the mobile phone, okay? It's a complete product, it's a laptop, whatever it is. It is not an IC, it is not resistor, capacitor, nothing. Okay, so it's the assembly, the total product is what is being tested for, not the IC. So I'm still not going into the topic of why IC EMC is important, but just to keep this in mind, that ICs are not to be CE compatible or FCC compatible. It's the product that needs to pass the test. Now, this is another thing that, again, this is more an evolution, it's more a trend where the industry is moving. Like, I've just shown you some applications here, right? Certain things are not listed just to not to make the slides too fussy. But in general, if you see like the frequency bands now from 3 Hertz, right, up to 30 gig and even more, like the automotive radar is somewhere in 77 gig, right? The new 4G, 5G technologies are all running in the 20 gigs, right? You have the current existing automotive radar is already in the 24 gig band. Like if you notice, the band is only increasing. The noise devices that are capable to generate noise in these bands are also increasing. There's no change in that. Then we have a lot more devices on, on this consumer electronics part, like Bluetooth and wireless and 5G, whatnot is coming in. Then the automotive radar I spoke about is just extending its frequency bands. And we have a lot of other, say, electronic equipments that operate in this wide RF band, okay? From 30 kilohertz, 300 kilohertz, more or less, to 30 gig. And you also have military and marine equipments operating using low frequency communication equipments to talk through because of the wavelength requirements in those implementations. So the main objective of this slide is keep in mind that the arrow on the right is only moving to the right. It is never coming back, right? Now, if it's moving to the right, it means a lot. It means that every device is operating in those frequencies, and an operation means you have to design for it. It's not simple. It's not easy to design RF in a small IC. So we'll go to those challenges as we proceed. Right, and this is another nice report from the Ericsson mobility document, right? This is very recent, I think. I just took it recently on 2020. Now, what is this report? Now, as I said, I'm not into marketing. I'm not going to sell the numbers here, right? The whole objective is that just notice the trend. As the years go on, right, there's more 4G, there's more 5G. And the 5G spectrum is expected in the 700 megahertz, which is what people are working on. Yeah, 3.6 gig, more or less slightly above 4G, and 26 gig. So they are working across different bands, right? So what does this mean? As I said in the previous slide, it means a lot in silicon design. There's a lot of opportunity here in terms of design optimization. There's a lot of learning to do for the whole industry as such. First thing is, as you go higher in frequency, right, you have to go into new technology, process technologies. There's no choice. There has to be miniaturization. There has to be tremendous scaling. There has to be a lot of strain, whatnot. There's a lot of integration going on because of multifunction, DSP, SOCs, whatnot, right? And then, of course, things have to be high speed and configurable. Like, for example, as I said, the 5G itself could be 3 bands. So if you have to make a system that has to work on all 3 bands, you may have to make things configurable as well, right? And finally, not everything can be made at any price. It has to be reasonable. It has to be, there's a lot of cost pressure going on in terms of design. So this is just an example in the 5G. The same thing holds true in autonomous electronics, autonomous cars, right? In Industry 4.0 system, everywhere, you will end up seeing a lot of high frequency problems coming in. Okay, so now this is a nice report. I should thank Mr. Excellency Colonel Alexander Boyer for publishing this in the conference EMC Com4 in 2019 in China. So this was a nice a chart provided by them that kind of showed how with technology that you see on the x-axis here, right, from 130 nanometer to say the futuristic, maybe the current 7 nano and the futuristic 3 nanometer technologies, and the amount of current drive in every MOSFET, right, every FET being used, right. So currently, look, up to around, I believe 20 to 32 nanometer technologies, MOSFETs are still being preferred as the device, right, for all devices, and then for all process technologies. And then below that, right, 1410, I think you can find this in a lot of Intel documentations. Like this FinFET, right, fin field effect transistors are being quite, let's say, preferred, right? And as you go higher, it's expected to be the multi-bridge MBFETs. Now, across this, you could see the way the green, the orange, the red, right? You can design devices for low power, general purpose, and of course, very high performance with a lot of course, design requirements on it. Now, the interesting point now, it's not about this technology. I think there are a lot more people who are much more, I'd say, competent to talk about technologies than me. But to this talk and in my perspective, the most important aspect is the current drive, right? The milliamps per micrometer, right? You can see a gradual increase as you go. Right? There's more and more current being driven from every MOS. Now, this means straightforward, I think, more current, more heat. I think a lot of us know about the thermal problems associated with this. Cooling is a problem, right? I think those things are all taken care of. People are constantly working on it. And people like me and other EMC guys in the industry are also interested in the magnitude of this current, because this current is going to be problematic in terms of EMC. I will share that with you next slide. So this technology, right? This technology evolution, what is the problem, right? So first thing is, because of a lot more integration and I'd say complex integration, you will end up having what I call as higher base emission, meaning you're increasing the standard emission from the IC itself slightly higher because there's just too much functionality on it, right? It's more compact. It's just more system on chip solution. It is more a solution rather than an IC only now these days, right? At the same time, you are also reducing, reducing the susceptibility, the standard ambient or base susceptibility of the device, making it more sensitive to failure. Like the more you add, it's more problematic to manage, right? And as we saw in the previous slides, the frequencies increase. Therefore, you end up having RF electronics. You end up having high frequency signaling, along with low frequency items. You still have to use a PLL, right? They're all very sensitive devices. You still have other low frequency items. You may even have to use LDOs on board, like for power supply, internal power supplies. So like that's classic design problems. And then you also add in the extra high frequency items in the same design. So that this causes this whole susceptibility problem, right? So the end result is that as technology shrink, as technology evolves, right, you end up, whether we like it or not, we end up reducing this compatibility margin. What is this compatibility margin? It is actually the gap between the susceptibility limit and the emission limit, meaning you don't emit high such that you start to fail. Same thing, you have to keep the limit such that you should manage the emissions somehow internally. You don't want a failure from the same IC itself, right? You don't want a block to kill another block, okay? So this problem has been consistent, like failures within the IC, failures between ICs, they all follow the same philosophy. So in EMC, our job every day, right, as designers, as system designers, as IC designers, the big job is how do you manage this compatibility margin? How much of emissions can be tolerated such that we don't tend to fail? Similarly, how to design the component to be good enough such that it can tolerate the emissions, right? So this brings us to this big topic of the role of the IC itself. So let me break down the problem. I'm just giving you an automotive example here. The same thing is applicable for every other field. Right? You have the end system, which most of us are aware of, right? We are users of these systems. Into these systems, you have equipments that go in, and then these equipments may have multiple PCBs, and finally you have the IC itself, right, which is going onto the PCB. So that's a subtle difference, right? In my, again, this is all in my school of thought, you know, ICs, multiple ICs can go into a PCB, and the PCB will have connectors, external components, whatnot. And then an application could have one PCB or multiple PCBs stacked together and put in an enclosure, right? This enclosure could be metallic, plastic. Again, it's up to you, right, based on the application requirements. And in the system, you'll have this equipment talking, you know, through using harnesses, or it could be even Ethernet communication systems. It could be USB systems. No, it could have any harness, right? It could have any wire connectivity. And worst thing, or best, it could also be wireless, right? Now, going by this scale, what is the emission problem? So it starts from the IC, right? So you will end up having currents and transients. I will just show this. Why do we have this? So IC is the source of the problem here, right? And then once the IC goes onto the PCB with external components, you will end up kind of moving the problem into the PCB. Currents will start flowing around the PCB. And then once you go to the next point, right, you will end up going between PCBs. You will start creating fields because the loop area becomes higher, right? And then if you have cables, you will start coupling that current, those voltages onto the cables. Cables are huge wires. Again, they would act as antennas and end up, you know, causing some trouble in the end system. Okay. As I said, the system could be anything. This is true, it's valid in the industrial communication space everywhere, right? So this is the emission front. So see this approach from a very bottom, the smallest part of the IC going up to the system, and how things evolve as you proceed, right? As you scale up in the development. On the immunity, it's the exact opposite, right? You start from a system problem. You have to understand how much of that problem is actually going to the equipment, breaking it down to how much of it is actually induced onto the PCB, what the PCB is capable of filtering. Like you have external components, you will have decoupling components, you will have some filter. And finally, how much of what reaches the IC. And once it reaches the IC, look, the IC has to be designed to tolerate those resultant energy. If not, the worst thing is IC malfunction or IC damage, okay? So in both the scenarios, the role of the IC is so important that one cannot neglect the importance of, say, EMC of ICs, right? No one can neglect EMC of system, no doubt, because as I said before, you have to go through the legal requirement, you have to go through EMC testing, right? There's just no back channel for that. But all the other things now, there's no need to do EMC as such. There's no so-called a legal requirement, but you still have to do something so that the system will meet the emissions. And similarly, the system is able to kind of do something that the IC is able to meet the immunity in the environment. Right, so why EMC of ICs? I think this is it. I think we've come to the core topic. So until mid-90s, right, IC designers had no consideration about EMC problems, right? This is even true in some ICs even today. That's the statement. EMC was handled only at system level, and EMC even today is handled at system level in some cases, but not everywhere. Many system problems were root cause to the IC. Okay, it took a while, but I think it was root cause finally to the IC itself. And at one stage, I do not know the exact year, but at one stage, EMC became the third common origin for IC redesign. Right, so you have design errors, you have electrical overstress, ESD, those failures, right? After that, EMC became the reason for redesign, meaning people couldn't fix the problem on the board. It wasn't possible to fix the problem at the system, right? Now, semiconductor manufacturers are faced with increasing expectation from the customer for designing ICs with good EMC, right? What is good EMC? Meaning you have to emit low, but be highly immune. And I think we saw this again with technology trend, right? Where you are reducing the size of the chip, you're increasing clock speeds, increasing complexity. ICs inherently are more emissive and more sensitive. We just cannot change this fact, right? So this brings the whole, the EMC of IC. And now another important thing is this document. I don't have the updated version of this, but that could be a few changes. In automotive, so there's this fact sheet from the German standardization group, right? wherein they have a slight difference, or slight, I'd say, differences between automotive semiconductors to consumer components, right? And two items are actually focusing on EMC alone. And again, I do not want to read through everything, right? EMC at IC level, right? In automotive, one is expected to do a lot of support, right? At IC level, and if the risk is not properly aligned, risk is not properly understood, the car OEM may not even implement the product, okay, because of a field return problem. As I said, I think as examples when we started off. So the impact as on an IC maker is that you need EMC experts who are solid in IC design, and they understand how to design this, how to use the IC in a system so that EMC is good enough, right? The same thing at system design, it's very similar. There's a lot of expectation from the IC maker that you do a lot of testing, you do a lot of support from the field, you have a lot of application engineers, whatnot. So this is a big problem in automotive. So automotive has been, I'd say, one of the toughest EMC environment. It is still the toughest EMC environment, and a lot of EMC design tools and things have come from the automotive world, right? So this is an important point. So don't forget, if you're an automotive electronic IC designer, it's a big deal to do EMC on it. So what is the trend, right? Again, as I said, this is, let's say, EMC critical designs, right? EMC concerns have moved from system level to IC level. That is clear understanding that a lot of system failures have been due to IC. Okay, the EMI EMC has to be taken into account at a very early design stage. Okay, and to do this, one has to rely on simulations and modeling. There is just no other go, right? So measurements technically and preferably should be done only to confirm good simulation. This is, I'd say, a hypothetical situation, but this is where we all want to be. Okay, we measure it just to prove a point. Okay, we know it's going to pass anyway, but we just want to measure it, right? And finally, it is very, very important to map system EMC onto the IC design. Like if you do not understand the system constraints, including EMC, we're not going to design the IC correctly, right? There's no point over designing or under designing. So one has to understand those requirements first. So automotive could be a different beast. Industrial electronics could be a different beast. Medical devices are a different beast. So we have to cater the IC design for each field of interest. Right. The good news is that we have many solutions for this. So starting with the famous, medical, I'd say, concept, prevention is better than cure, which is something that we are all talking today in the current environment. In EMC, the same logic is true. The first thing is attack the source. How do you change the noise characteristics at the source? This is at the IC itself. This is where design becomes very critical. What can be done in design to improve the noise characteristics, to reduce the emissions, to make it more immune? So this is always the first option, but it's not always possible to do everything either at source. The other option is to improve the immunity behavior of the receiver or the receptor, the victim, or what you want to call it. And the last thing is breaking the coupling path. So if you think that, say, for example, there's coupling on the board, you can optimize the board design a little bit, move the ICs far away. If you think there's coupling happening in the IC, you may have to design it correctly. Placing the IC floor plan could be critical. Now, having said this, all this seems logically nice, right? But how do you do this? Does this require a magician to do this? Now, again, EMC has been long seen as black magic. It is certainly not black magic. A lot of this is clear understanding of the design. So I'll show you some examples in my last 12, 13 years of working in industry. I'll share some examples of how EMC problems have been debugged, right? And yeah, this is a use case in I don't recollect exact setup. This could be a set-top box or something like that. Okay, it's a big device. You can see a huge PCB with multiple PCBs, connected together to make it work. So this board had some kind of an emission problem. I don't recollect the exact frequencies, but yeah, it started radiating in the system testing. And what we did is straightforward, right? Go to the IC, take the IC there, as you see the zoomed in section here, and we do some level of emission scanning. So this is using a near field probe. You can see a small probe that's used to scan. So you scan around the IC here. Okay, and once you scan, you can start mapping onto the floor plan, the design, and see what is actually radiating. A result of this is just shown in the next slide, right? You see different components of the fields like the Hx, which is the X component of the magnetic field, the Y component of the magnetic field, and the Hz, right? Like if you notice, at different frequencies, different parts of the chip radiates, right? At 27 meg, the top right is radiating. At 30 meg, the bottom right is radiating, right? The 135, it's again more or less a harmonic of 27, right? At 450, which I said I don't recollect exactly, it could be the clock frequencies inside, but you could see that it's more the core itself, right? It's just everywhere, okay? So this is very important. So one knows, right? Okay, I see fields emitting from this side. It could be coming from this bond wire, or that part of the chip, or that block of the chip. So you can break down the problem using proper tools. Again, these are all not standard tools that we are used to, like oscilloscopes or probes or whatever. These are sophisticated tools. They have to be used differently because of the frequency involved. We have to scan up to sometimes 1 gigahertz, 10 gigahertz, depending on the operation. This is just, what seemed to be black magic just earlier has now become more understandable after this level of debugging, right? And then another very interesting thing that came up very recently is a use case where, in a DSP, you end up seeing tones, right? Clock tones actually coming out in the GPS and other bands, right? In the 1.5 gig, right? Here, somewhere here. Now, again, it's a system problem, but how do you understand if it's from the IC or not? So we had to do some analysis. It took a lot of time to understand this problem. So we used a different test here. It's not the near field scan. It's more of a, let's say, a scan over the IC in general. If you notice, like an interesting topic here is we had a 112.5 megahertz clock running, right? It was clocked out on a wire on a pin, and 112.5 is 100 megahertz. It's quite low frequencies, but you could see the harmonics of that coming up at the GPS band, the 1.4 gig plus 2 gigahertz. Now that's the 10th harmonic and above. So even the 10th harmonic and above is strongly radiating, right? And when that thing was disabled, when that function was disabled, there you go, it's down. You don't have those points radiating anymore. So you can see how design is directly contributing. If you just enable some functions, it won't meet the limits. If you disable it, it meets. So there is something in design that has to be fixed. This is not outside the IC. This is happening from the IC itself, right? So this is another interesting example, right, on DSP. And finally, how does this come in, right? Then we went on to understand, where is this origin? Okay, we see the peaks, right? We are seeing fundamental frequencies and harmonic, but why are we seeing peaks in the 10th harmonic, 15th harmonic? Is that normal? So as you go back, go around into fundamental VLSI design, this is just an example of a buffer. You see how, this when you do switching of the gates, you end up, driving current through the cap, and then when the other gate is switched, you end up dissipating the current. Now, every time you do this, depending on all the parasitics involved, all the resonances of this capacitor, along with the, say, the parasitic inductances and whatnot, capacitances across the MOSFET or any other FET, you end up creating these spikes of current. So this is the DI dt. Okay, so these currents, the DC level could be what you want. It could be a few tens of milliamps of 1 milliamp per gate or whatever it is. But you end up creating spikes, transient spikes at every second, every time a second or whatever you switch. Okay, so that transient, when you take an FFT of this, you end up seeing all this funny spectrum, and this is the problem. And the reason why I wanted to bring this circle here is that, okay, so all of us know the Fourier series of a simple trapezoidal pulse or whatever it is. It has to scale down by 20 dB per decade or 40 dB per decade. But what happens here is you see a sudden increase at high frequency. So why is this increase happening? It could be because of another harmonic somewhere present that we don't always see. Okay, so you may not have just one fundamental frequency. You could have other parasitic resonances coming in the design itself. Okay, so this is typically the parasitic problem causing the emissions from the IC, right? And just to show this in the technology perspective, as technology scales down, as we go to a new process, we are going faster. This is an example of how, old process, there'll be a dVdt or a dIdt, right? The blue one. In the new process, the dVdt and dIdt is much more faster. Right? It's more rapid. Again, I don't want to go into fundamental Fourier series now, but if you go and study this, this will directly impact the slope or the fall of the energy in the frequency domain. Okay, so faster switching speeds means stronger dVdt didt, and invariably you will have high parasitic noise. One cannot change this physics of it. But having said this, how does this end up radiating then? Okay, so I've given you an example of a few cases. Like, so once you have an activity happening on board, right, somewhere here, you can see a lot of fields exciting the bond wires. Okay, once you have bond wires in the package and whatever, depending on the package, those bond wires now act as antennas at medium frequencies and high frequencies. So this is one typical problem. Same thing on the right, you can see the scan of a DSP overlaid with the say the bond wire diagram of it. Same thing at one section of the chip, you can see that the fields are all concentrating on towards the bond wire. It could be the supply, it could be anything here, right? It doesn't matter. Okay, but you can see how the energy working in it, the blocks that are operating somewhere here, and those blocks are exciting the bond wires, and the bond wires end up radiating. And how do you represent this? I've just shown, just for the sake of it, you can see how one can represent this as a part of a simple equivalent model, right? You model all the bond wires using inductors and resistors. You have to model the coupling using capacitors. You could do overall capacitance of the die, of the gate, whatnot. And you can excite, you can use an excitation source to create this problem. Okay, so this is it. So this is the reason why the ICs radiate. Okay, in the previous examples, we saw cases where you saw radiations happening at very high frequencies. What would have been thought as a system problem is no more a system problem. It is actually a radiation from the IC itself. Okay. Now on the immunity side, I think one can just look at it slightly in the opposite side, right? It's the technology scaling down, right? You have low power consumption, which is a nice thing, but whether we like it or not, we end up also compromising on the noise margin, right? The lower the voltage as you go, right, the noise margin is also very, very low. Okay, so what you see on the right is a nice thing to have. What is on the left is also a nice thing to have in terms of design, in terms of implementation, but it compromises immunity. Right? It is something that we have to work with, because this is what we have to do, and we'll have to fix the problem, fix the design such that we are more immune to this, or managing this noise margin problems. Okay. All right. So what are all the parameters? So this becomes an important aspect of both IC design and system design, right? The parameters influencing IC susceptibility, like starting from the left, you see you have the PCB here. So you will have the PCB parasitics influencing the whole effect. Now you may also have external passive components. Of course, all of us know we need decoupling capacitors and sometimes ferrite beads and whatever. So those components will do some of the filtering, but is it enough? You may have resonances coming there. Again, how much of what is filtered, we don't know unless we study it. Then once you get into the IC, just at the package level, you will have a lot of, say, filtering happening because of the package parasitics, because of the package pin capacitance. It may help sometimes it may make things worse if the resonances fall in the wrong frequency band, right? And then once you get into the IC die itself, you will have the impedance of the IC block, impedance of the pin involved, the pin inside the IC, I mean, right? And then you can have inside, you will have a lot of nonlinear effects. It could be, for example, diodes, it could be ESD diodes, it could be the pull up, pull down, whatever. You may have conversion of RF noise into DC offsets because of simple demodulation effect or rectification effect of diodes, right? And finally, yeah, this is the worst thing that could happen is inside the IC, between blocks, you could have the block's own susceptibility. One block could be very sensitive compared to the other block, or the block could be positioned such that it is near a highly really emissive block. So the emissions from the previous block is hurting the next block, right? So you can see now within the IC, right, you can see how noise can propagate, and yeah, you can see a lot of energy coupling between some hot zones here, some hot zones here, and you still have a lot of coupling happening in areas where we are expecting no energy at all. And this is sometimes not good, because if for example, this bond is connecting to a sensitive thing like a PLL or whatnot, you end up coupling onto the PLL and doing something funny on the chip. So this is critical, right? So one cannot neglect this feature in the IC. So how do you quantify this? There are methods to quantify this, and I'm just showing an example that was published in a paper a few years ago. This is an LDO. a simple LDO IC, right? It's minimal decoupling. Okay, you have minimal 100 nanofarad capacitors for functional requirement, and that is it. No EMC filtering, no nothing, right? You can see now our target was 40 dBm, which is the max, right? I'm just giving a number. When we inject noise, right, on the input pin of the LDO, you can see on the output, you have a lot of failure happening. This is pass fail on the output. So of course, LDO, the output should be, say, I don't know the exact number, it should be 5 volt. On a 12 volt input, we are expecting the output to be 5 volt. But when the noise, for example, at 10 megahertz, I'm giving a number, when the injected noise was more than 10 dBm, 15 dBm, whatever, this will drop to less than 5 volt. So it's a failure, right? Anything below this number is a pass. Anything above this number is a fail. So you see, we are nowhere near a target. I don't know the target. It could be 30 dBm, it could be 40 dBm, depending on the application. But end of the day, we quantify the susceptibility like this. We know how much the part is designed to manage. Either we go back to design to improve this value, or we look into opportunities where can we do some filtering outside? Can we add an extra decoupling? Can we add an extra decoupling at the output to filter the noise, whatever. So you may have to fix the problem either at the PCB, if possible. If not, if it's an inherent problem at the IC, you may have to fix it at the IC in the design itself. Okay. This is how you quantify the susceptibility term. So you kind of plot this curve. Okay, now what is this IC with improved EMC? So let me finish. I think I'm almost done here. So at board level, this is what it is. I think a lot of EMC engineers today in the industry know this, right? EMC at the board level, PCB layout is very critical. PCB floor plan is important. Okay, selecting the right components for filtering is important. The mismatch tolerances on the component, the use of external RLC filters, external ESD protection, sometimes shielding the whole board or the PCB or the IC specifically. So these are all tricks, I'd say, used in the EMC world for many, many, many years to get things going. Right, so the system meets EMC. But what we are all working forward is something, or looking towards is something like this. At IC level, why don't we extrapolate the same thing on the board level in the IC? Like, why not look at the IC layout itself? How about optimizing the floor plan such that we place blocks at different locations? Okay, then how about placing the RLC filters on chip if possible? Optimize the EMC, develop some IPs that different companies have, right? And optimize them for EMC, and finally have software filters if need be, right? And then package pinout is important. I think we saw that a few minutes ago, right? The package will radiate. The type of the package is important. So you're talking about different package types within LFCSP, right? You can have QFN, you can have that, you can have this. End of the day, different packages will radiate differently because the parasitics are different, right? A BGA could be different, LGA could be different, a QFN could be different. So we'll have to understand and optimize. Pinout is the next same concept. 2 pins next to each other will couple. So while choosing the pins, the power supply ground should be coupled properly. If there's a sensitive signal like a clock line or an emissive signal like a clock line, they have to be moved away so that you reduce crosstalk, you reduce coupling between the pins. Protection, same concept, right? This is very important so the chip does not get damaged. And finally, looking into options where you can shield the whole IC internally, not outside the board, inside the board, inside the chip, right? All right, so what do you have for measurements? So I don't want to go into all these standards here. I'm just giving you a sort of estimate of what has been developed in the industry over the last, say, 12 years, not more than that. A lot of these standards here are not too old. They're only about 10, 12 years old. Okay, so you can have different techniques to measure. So you have two framework standards called IEC 61967 and IEC 62132. Okay, so these things, 61967 is for emission and 62132 is for immunity. Okay? And you can see different ways to measure it. This is what is called a TEM cell. This is what is called an IC strip line. This is what is called a direct power injection technique, wherein you want to inject at every pin. Okay, and this is a CE method, the emissions method, to measure the emissions from every pin of need. Okay, so yeah, there are methods that are standardized so that every IC maker can make use of these techniques. Similarly, modeling, you have a very similar framework. It's called 62433-3. Sorry, 62433 framework. So you have the -3 model, -2 model, and -4 models. Okay, and some of the models are still under work. They're not yet published, but they will be published soon enough in the next few years to come. And as I said, These are even more recent, like these measurement standards are at least 10 years old. These are all only 5-6 years old. Okay, so a lot of research is ongoing on this topic of how to design, how to help design for EMC inside ICs, and how modeling can help mitigate those things, right? And if you take a look in every model, right, you will talk about bond wires, you will talk about parasitic capacitances, parasitic inductances, and everything. One cannot neglect the package, the bonding, and the block itself. Okay, it's very, very important. That's why the system core simulation is important. Understanding the external decoupling is important. The overall system understanding is very important for IC design, right? Now, in terms of people and tools, right? I think this is a very common thing. If you talk to any EMC guy in the industry, this will be a common point. In terms of people and human resource, there's a lack of EMC engineers with knowledge on ICs. You have EMC engineers, system engineers, they know how to solve a problem like shielding and this and that. But how do you translate that into IC design? It's not an easy topic. You don't have many guys doing it, right? There are not enough engineers who can design and simulate chip, package, and board together, right? And there are not enough EMC engineers who can handle signal and power integrity together as well, right? A lot of project management is also non-EMC aware. That's a fact, right? EMC is a tough topic. It takes time, it takes cost, and whatnot. In terms of tools, I think this is a common problem in many complex simulations. Data sharing between different parts of the IC, because the package could be designed by someone else, the PCB could be designed by someone else, the ICs, the designer could be designing the digital, there could be a digital section, analog section. So the data sharing between blocks, between the same company, between different companies may not be straightforward. So how do you share models and do the work, right? And even if you end up sharing, given the complexity of today's ICs, it could be very computation intensive. So not sure if the tools can manage it, right? And finally, making things efficient for a Terra device, like multi-device, multi-gate problem. You don't have the tools today, but tools are currently in development. To show you some of the tools, like some of these tools, you might be aware of this already in different forms for different use cases, like the multi-physics problem and whatnot. For EMC, these are the common tools. Now CST is no more CST, so I should change it. It's the TESO, right? TESO group who owns CST now. But in general, you have different tools that are available for electromagnetic simulations. And what all these tools do in common is they all resolve the electromagnetic fields using Maxwell's equations. So me and you need not have to sit and write all these equations ourselves. It's all done by these tools. All we need is import the models, import the 3D structure, get it as close as possible to reality at the IC level. And you can also extrapolate that to a system level. You can import a car's drawing. You can put in the harness wiring. You can see an example here now. I'm just exciting a small wire that's under the chassis of the car and seeing how the field is distributed across the chassis of the car, the whole body. It's just one single wire excitation can have a lot of radiation. I don't know, I don't recall the exact frequency here. It could be, I don't know, maybe 40 megahertz or so. But look at this radiation here. It's just spreading everywhere in the car, right? Okay, so tools are nice. It's very, very good to actually help us understand the problem and optimize the system. Right, and to just finish up, let me show this. As electrical engineers, we are all aware of the terms on the left, like voltages, currents, impedances, and whatnot. On the electromagnetic domain, these terms are translated in a different form, in a different unit. That is it, right? A voltage, you should see a voltage could cause electric field. You should see current causing magnetic field, right? Impedance is called the characteristic impedance, which is the famous 377 ohm that we talk about in the open field, right? In the vacuum. And Z0, again, impedance is the ratio of the electric field to the magnetic field. And finally, the pointing energy, the E into H, gives you the power. So it's quite linked. Okay, it's very closely linked, right? So voltages will cause electric fields and currents causing magnetic field is something we'll have to understand. And this is a very important understanding one needs to have to, be an EMC engineer and move from an electrical engineer to an EMC engineer. Okay, in conclusions, let me finish in a philosophical way. Whatever can go wrong will go wrong, and that usually happens at the worst possible time, right? And this is very, very true in the EMC world. And one more very important thing is you cannot successfully determine beforehand which side of the bread to butter. The chance of the bread falling with the buttered side down is directly proportional to the cost of the carpet. Okay, so EMC sometimes falls into this category where you don't know when the problem will happen, and when it happens, it will be at the late stage A car maker might want to release a car, and that is when EMC problems come in. Now, the release has to happen. How do you fix the problem immediately? So it's a tough game to play sometimes. So it's very important that we endorse this fact that EMC problems are ever growing, and the IC is an important player. Industry needs bright minds to manage the EMC problem in an efficient way in the years to come. Right, EMC expertise is growing at academic level. There are a few courses around the world now. Industry experts go teach EMC at different levels, system level, IC level, and everything. But it is still slower than the rate at which problems arise. This problem will be solved over time, but a lot is done through experience, naturally, like any other growing field. And system, IC, EMC are closely mapped. As I said, I think some of the examples have clearly shown that a system EMC failure is because of an IC failure. And so EMC should be a part of IC design, and one cannot neglect this in EMC critical applications like industrial, automotive, sometimes in medical, right? So with this, I think I am finished with the talk, right? I'm open for questions and ideas, and look, any collaboration I'm happy with. Thanks, guys.
Thank you, Dr. Abhishek, for a wonderful lecture on EMC. We could see a couple of questions in the chat box.
Yeah, I'll open it up in just a second.
Or if you want, I can read that.
No, this is, I think I'm sharing the chat here, right? If it's fine.
Yes, yes.
So how to reduce the IC radiation? Can the IC be integrated with new nanomaterials to reduce heat radiation, right? So in terms of radiation from the IC, I think it goes a lot with the drive strength, for example. It goes a lot with the block design, right? If you want to reduce the emissions, right, emissions from the IC, yes, one concept could be using new materials, right? Because new materials will have some materials. I think the SiC is a very good example. I can give you the silicon carbide material has a more smoother switching characteristic than, say, standard MOSFET. Okay, standard silicon or germanium MOSFET. So it depends on the technology itself. So one needs to first quantify that, right? What is the dVdt? What is the dIdt, right? And then optimize it. And the second thing, I think it's a very common item. You might find it in some data sheets, right? Is what is called a SPED spectrum, right? What you do is you have a frequency, like say 10 megahertz. Now, instead of clocking at 10 megahertz, you can actually jitter the clock, say 9.5 meg to 10.5 meg. You can keep moving around with the clock frequency such that you don't have a single peak. You more spread the energy. It's called that's why it's called the spread spectrum method. Of course, you can do this at, say, medium frequencies, say 1, 2, 3 megahertz. You cannot do this at 25, 30 megahertz. It's a problem. You could manage to do it at 100 megahertz, but you have to be good in design, right? So that's an important aspect of design. And yeah, of course, the package is the next big deal, right? So designing the IC is one thing, but if you design it great and you choose a very poor package, right, that's it. Right? And there is enough evidence in the industry. If you can go and look into some IEEE papers, some people have done the same die, the same IC in 2 different packages. The BGA package, which has, say, less bond wire length, and a QFN package. QFN will have lead frame, right? Just comparing the same die, same function between 2 different ICs, you will see one radiating more than the other. Okay, it's the same design. Maybe the BGA is more expensive, but it will still meet all the IC emission levels, but the QFN may not, because the QFN has more bond wire. So that's an important aspect, right? So it's as I said, it's a big topic, right? I don't have a straight answer to this, how to reduce the radiation, but you have to do at multiple stages of design. Right. The next question is, can ferrite beads be used on the IC? So this is another huge problem. So currently, there is no process technology that helps do magnetic materials in design. Okay, ferrite bead is a magnetic material. It is complex. It is not possible. It is tough, right? Now you do have the many chips now, or in the SIPs, the system in package technology, where you have a laminate on which the die is placed, right? So you have a laminate. So let me call it as a PCB, right? You have a small PCB inside the same package, and that PCB can hold ferrite beads. So there are guys now in the industry who are making chips in a single package, multi-chip in a single package with external components like ferrite beads and even decoupling caps. The 10 nanofarad caps, 100 nanofarad. You may not be able to put in a huge 10 microfarad cap on chip because of the height of the capacitor, but you could still manage to put in small caps and small ferrite beads inside the IC on a laminate, but not directly on the bond wire or on the die. It's not yet available. Yeah. Did I miss any question here?
Yes, I think all the questions are being added. I mean, one
Just
question
one.
is the last. There
Yeah.
is
the IC and PCB industry. I don't fully get this question. Can someone explain this to me?
Is the IC and the PCB is there in industry?
Yeah.
DCS, BOR, SCADA, PLC, VFD slash HMI as well. I think he or she is trying to ask whether in industry are they using PCB or PLC? Is that the question? I believe so.
Yeah. So let me I'll try to answer this to what I understood, right? So what I can see in industry is that the choice of the PCB could be very different depending on implementation, right? Like even the PCB is a big topic again, right? PCB can be a 2-layer PCB, could be a 4-layer PCB, okay? And this human machine interfaces and PLCs, now they're all different. I'd say in the industrial environment, it's a commonly used one. Okay, human machine interface is something that we have in the car, right? The whole front screen, display screen in the cars today. Now, depending on the implementation, the PCB choice, the PCB selection, the ICs mounting on the PCB, they're all very different. I don't think there's a common answer to this. But yes, people are aware of these problems. People take into account the IC and IC selection, the PCB selection, the PCB quality, including thermal quality, as they work on these implementations across the industry, right? And one last question here. So does BGA package reduce emissions, right? And that's a nice question. No, not always, but generally yes. Okay, it depends on how you do the BGA. Even in BGA, you have different types. You have fan out, you have fan in, right? Fan out means you have, you still have bond wires inside the BGA, whether you like it or not. Once you have bond wires, things may go bad, but one needs to have bond wires because of the fact that you have more number of pins to manage. You have to wire them out. There's no choice. So BGA package is generally better in terms of emissions, is generally better in terms of performance, because inside the BGA, you have a nice ground plane. You have a laminate. So the laminate will provide a nice common ground and you end up having a good performance in general. But BGA, you have multiple types and some are much better than the other.
So two more interesting questions is also there. One I could see, are the PCB and the ICs are manufactured with the help of 3D printers?
I really don't know.
So this is an interesting question. Probably.
ICs not, but PCB probably yes, but I don't know.
Yeah, no. Even as far as I know, I don't think so. But
I don't think
it's a good idea.
Yeah.
It's a good idea. Then the second one, what was the question is like, if the IC does not clear EMC, the IC is abandoned?
The design is abandoned. So the design is not abandoned. So what generally is done is either we work towards fixing the problem on the PCB if possible. If it is really not possible to fix the IC, we go back to design. The IC is redesigned if it has to be. There's no choice, right? But of course, if it doesn't meet, the next step is obviously go to the PCB and see, can we use an extra decoupling cap to fix the problem, or extra inductors or whatever on the PCB to fix it.
Yeah, nice. I think fine. Okay, thank you, Dr. Abhishek.
Yeah, thank you, Mr.
joining us.
No
it was a very nice session.
In fact, it was interesting and new topic for all of you.
Thank you. Let's see.
Thank you.
I will call you
thanks
later.
A lot. Thanks a lot, everyone.
Thank you for joining.
Bye-bye.
Thank you. So participants, we have enabled the poll. I think you can just finish the poll. We are just about to end that poll. Please make it fast. And yeah, with this, today's session has been coming to an end. Following this, we have a technical presentation. That is track 1. We have this list of papers those people who are in that list, please ping me in the chat group chat. That is paper ID 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Professor Saurav? Professor Saurabh Nahar, I have made you. You can just unmute and you can speak.
Yeah, so hello, good afternoon, everyone.
Good afternoon.
Welcome to the session.
Yeah, I am also looking for Pradeep. He said he will be joining. Professor Pradeep is there. 1 minute.
Wait or should we start?
Yeah. He is there. I am just making him as a co-host. Professor Pradeep, you can unmute and you can speak.
Good afternoon, sir.
Pradeep.
Good afternoon, everyone.
Yeah, good afternoon. Whether your camera is...
Okay, I'll just turn on in a minute.
Yeah, please.
Yes, sir.
Oh, fine. So I could see here paper 12, 2, 1, 7. So there are 4 papers available.
Okay.
So probably Professor Saurabh and Professor Pradeep, you can take up this session. So the rule is something like you can allocate 12 minutes, like 7 plus 5. 7 minutes for their presentation and 5 minutes for the question from the audience as well as from your side.
Okay, sir.
Okay.
Okay.
So the other things, you both 1 minute, I can just share the evaluation sheet also. Probably I can let you know.
Okay.
Professor Pradeep and Professor Saurabh.
Yes, sir.
Yes,
you
sir.
can just evaluate in this fashion. For novelty, you may give some 10 marks. Paper structure formatting, maybe 10 marks. Results and application, 10 marks. Reference and its citations, proper citation, 10 marks. The overall quality of the work, quality of the paper work, that you can give 10 marks. So you can evaluate with a scale of 50. Or if you want some metric to be included, we can also include that.
Is there a detailed one on how we have to evaluate?
That's left to you both. I believe, professors, you might be knowing to evaluate the standard. You can just follow your own metrics, but probably within these metrics, or if you want some metrics to be added, you can do that also.
Okay, sir.
Is that okay?
Yeah, sir.
Okay. So, right. As of now, I believe roll number 1, 2 is there, 4 is there, 5 I don't see there, 6 also I don't see there, 7 is there, then 12 is there. So professors, you can start asking them. I am handovering the session to both of you. So you can just see the chat box where you could see the list of people who are ready to present. You can just ask them one by one to go ahead. So I will be a silent observer over here. Is that okay, Professor Pradeep and Professor Saurav Nagar?
Yes, sir.
Yeah, please, you can just take over. I have made you as a co-host. So if you want someone in that group to present, you just make them as towards your right. If you move, you could see more option. In that, you can make them as a co-host and ask them to share the presentation. Let's try one. Let's see the first gentleman with paper ID P001. That's first one from Priyadarshini Engineering College. Are they available?
You just sent.
Yes. Hello. You can just ping me under which name you are there so that I can unmute you.
Under S. Priyadarshini, sir.
Is it Priyadarshini? Is there anything visible here?
I have unmuted.
Yeah, all are in unmute. Okay. This is there. I'm making them as a co-host. 1 minute.
Okay.
Yes, you can just right click. I think you can also do it. Hold on for a second, ma'am. Professor Pradeep.
Yes, sir.
You could see on your screen, like
Yes.
if you want to unmute someone, you can do it. Can you try? Just try. Let's see whether it is working. You are being a co-host. You could do now. You could go to their name, and there are 3 dots, and in that, if you make them as a co-host, then you could see they'll be getting the privilege of unmuting their mic and sharing their content.
Okay, for me it's not working, sir. I have to just request them. That's the thing. I'm using the mobile app, so in that I could see a right arrow.
What about Saurav? Saurav, can you try?
But I am not seeing the co-host part. I can see the ask to start video and ask to unmute.
Yes.
No. What I'm saying is, Saurav, you can just see some name, go to their name, and at the end you could see 3 dots. Do you get something like make co-host?
So I'm not getting the make co-host option.
Okay, let me do one thing. I will make you as a host and then get back. 1 minute. Yes, now you try.
Yes, so now it's working.
Yes. Now you have the whole control. Like whomever you want to enable, you can enable them as a co-host and ask them to share.
Yes.
Yeah, please.
The first presentation is Priyadarshini, ma'am.
Yes, sir. I can hear you, sir.
Yeah. Can you please share your slides and start your topic is real-time peer-to-peer energy sharing using cyber-physical system in university campus.
Shall I start, sir?
Yes, sir. Yes.
Yes, ma'am.
Yeah. Good afternoon to one and all present here. I'm Priyadarshini, Assistant Professor, AAA Department from Hindustan University. I'm glad to present our work titled on real-time peer-to-peer energy sharing using cyber-physical system in university campus. My co-authors are Mr. R. Karthikeyan and Dr. A.K. Parvati ma'am. So here is my presentation outline. It starts from introduction, objective, literature review, and so on, and ends up with the references. So to give an overview of this paper, as we all know that the World Research Forum has predicted that the fossil fuels like coal and gas resources will be exhausted in the next few decades. So it is our responsibility to take initiative in using renewable energy resources as much as possible to conserve the energy for the future. So in recent times, we could see the gradual increase in the use of rooftop PV system and windmill system. With that, we can make the microgrid for the smaller community. So in this microgrid, the residents with these resources are able to consume, produce, and export electricity to the microgrids. They will be termed as the prosumers here. So this will lead the peer-to-peer exchange of excess electricity using smart net meters termed as the smart grid communication. So the general reliability issue will be there in the traditional grid. So to avoid this, the energy sharing is being proposed among the neighbors to avoid the transmission loss and increase the utilization rate of the RES. So the main challenging aspects are here to we have to keep track of the energy transaction and renewable energy generation because it is keep varying, and to compensate the buyers. So we propose some algorithms based on the cyber physical system, which is used to coordinate the neighbors and to collect data from the homes using smart meters. So here is the objectives. It starts from integration of various renewable energy resources to supplement the main grid, and design and implementation of battery management system, which will keep track of the charging and discharging of the battery to prolong the lifetime, and the development of real-time energy management system to improve the utilization rate, and design and implementation of cyber physical system based on the improved MILP algorithm. So the literature review, the first paper deals with the two-layer stochastic model predictive control scheme. It is based on the two different time scale of the microgrids, that is of sampling time. But the drawback in this is they will get a temporary optimal solution and to compensation of the forecast error. The second paper is based on the Nash bargaining theory, which will encourage the trading and fair benefit sharing. So it is fully based off the bargaining based energy trading, and this they didn't touch upon the role of power grid operators. So this is the pictures for future grid optimization. When we need to increase the renewable energy penetration into the existing grid, we need to create some microgrid which consists of energy storage system and the distributed energy resources with modern communication technology, which will transfer the data between the generation and the grid. The second picture is for peer-to-peer energy sharing. This the mainly the communication network and the automation plays the key role in the smart grid for energy transmission problems. So the novel concept of demand side management of the smart grid, which will increase the involvement of the end users in implementing the energy management actually. So these are the work plan and the methodologies. Peer-to-peer energy sharing, smart cyber physical system, and real-time implementation. In peer-to-peer energy sharing, we will formulate the prosumer and consumer management and energy storage renewable energy support. Here in smart cyber physical system, we do data acquisition with smart meters and cost optimization and load sharing. In real-time implementation, rooftop PV system and wind connected system will be implemented along with the IoT and CPS based energy management system. So this is the block diagram of the proposed smart grid architecture. We have 4 prosumers and consumers are being connected. Here the prosumers has been equipped with the renewable energy resources like wind and solar. Also energy is being stored for the future use with the help of this battery management system, that is BUU, and the DC power is being converted to AC power with the help of this inverter. And there is a black line that is a common power line. It is being designed for sharing the power between the prosumers, and the red color dotted one shows the communication line established between the system for sharing the data from load center to the central cyber physical system. So here what is the work done by cyber physical controller means it will compare the generation and the demand of the loads and decides the solution based on the comfort setting by the users. So in this paper, we have developed the algorithm based on the mixed integer linear programming and MPPT based implementation using MATLAB. It is because it has been used for obtaining the most optimal solution for the problem with a given constraints. So here we have considered 2 scenarios. First one is energy sharing algorithm with satisfaction ratio. The second one is energy sharing algorithm with satisfaction ratio and multiple sharing. So the left hand side is algorithm 1, right hand side is algorithm 2. The algorithm 1 is based on the surplus power and demand power. When the surplus power is greater than the demand power, the decision being taken there, only 1-to-1 sharing is being allowed. Like one home can share the power to the one more home. So in the case of algorithm 2, one system can share or accept the power from 2 or more system if it has excess power after giving it to the first system. So here we have developed some simulation model in MATLAB to analyze the PV system and the wind turbine system to obtain the optimal level. The first one shows the PV system and the second one is wind turbine system. And this is of a hybrid system with battery sharing. We have taken 2 prosumers to see the sharing of the power. And this is the pictures of installed solar PV system and the wind turbine system. We have used a PMSG generator for the windmill and battery management system. Here some slave controller has been connected across the battery terminals. And MPPT charge controller we have that is being connected between the solar panel and the batteries to control the charging current of the battery. So we have considered 3 smart homes and different demand profile. The table is being given for the load samples for each homes here. So this is the load flow diagram of algorithm 1 and 2. And in this table, we can observe the total electricity cost of the 3 smart homes in the microgrid is being gradually reduced by using the algorithm 2. And the cost of the home 3 is being increased due to the storage of surplus energy in the battery, because when the home is not being connected to the load, we can also use the surplus power to charge the battery as well. So here in algorithm 2, which will improve the SOC of the battery and reduce the dependency on the national grid. So this is a wiring diagram of the energy meter.
Sorry to interrupt, ma'am. Please finish it quickly.
Yes, 2 minutes. Okay. So in this we have AC bus bar and also we have a manual changeover switch for the additional safety purpose. So the real-time energy management system. We also have developed the web portal for the monitoring the battery system. It will monitor the voltage and the current SOC level of the battery. And this is for energy management system. This will view the load details and energy storage, energy sharing details and all. So these are all the hardware details which we have been used. And this is for the load curves of the system in real time and load sharing in real time system. Also, we have additional features so like notification for sharing, and we will receive the message alert for the low voltage and overcharging of the battery. So based on our comparative analysis, I would like to conclude our proposed cyber physical system will improve the performance of the prosumer and reduce the payback period of the solar PV system and windmill system. This collaborative behavior of the energy balance can be easily addressed and achieve the independency of the utility grid. So our CPS system will adapt the future smart grid to face more challenges, and the reliability will be more high. These are all the papers we have referred, and thank you for the patient listening. Thank you all.
Thanks for the presentation, ma'am. I have one quick question.
Yes,
when you tell about cyber physical systems, how about the security of these systems? Because there are some man-in-middle attacks that can happen,
yes,
and this can be disastrous once we talk about home management, power or security, whatever reason it may be.
Here for cyber physical system, we are also developing blockchain technology. So there will be some common ledger will be there. The blocks is being connected, which means like all the data will be connected in a chain. Like so, in between you can't have any outsiders to come and hack it over. So blockchain technology we can implement for the cyber physical system, sir.
Okay. Are you also working on the algorithms for blockchain technology, ma'am?
We have started working on it, sir. Like so many algorithms is there for developing the blockchain technology. So
Yes.
yes.
Okay. Okay, ma'am. We have got one question in the chat box.
Right. I'll just stop presenting.
Yeah. Can the smart meter be hacked and the grid will be overloaded? Is it possible? That's the question, ma'am.
To my knowledge, the smart meters can't be hacked, sir, and like grid will be overlaid. No, sir, grid will not be overloaded. Based on that, only we have developed this battery management system. So, if one like the loads will be 3/4 of the battery management system, sir. So, like if 2 kilowatt means 2.5 kilowatt generation will be there. So there won't be any overloading happens in that system.
Okay. No further questions means we'll close the session, ma'am. Thanks for your presentation.
Thank you, sir. Thank you so much.
So the second talk is 3002 from China. Anu, are you present here?
Sir, she is asking permissions to unmute her.
Yes, sir.
Okay.
Yes. I've made you the co-host. You can unmute yourself and
Yes, sir. Yeah, can you
share
hear
your
me?
PPT.
Yes.
Thank you, sir. Okay, let me share my screen.
Just before you start, please finish it within the time constraint of 7 minutes.
Okay,
And we have time for questions. And if you have any questions, please write it on the chat box of the presentation. And at the end of the presentation, we can
okay, sir. Can I
share
share
your
my screen?
PPT. Yeah, you can share your
Sure.
PPT.
Good afternoon to one and all present here. So this is M. Shaina Banu, doing final year ME Communication System in SA Engineering College from Chennai. So my work is to design the high gain low noise amplifier for the wearable devices network. So I've done this work under the supervision of my guide, Professor S. Suvita. So going on to my work, basically low noise amplifier is a very important receiver front end. Here, this paper particularly presents the LNA for the special application, that is wearable devices. So nowadays we use so many wearable devices like uh, wearable smart watches, smart coolers, Fitbit kind of things and all. So those comes under wireless body area networks. So with that, in order to approach that as my application, I've designed the LNA. So as the name insists, it is in low noise amplifier. So I aimed at two things. So being an amplifier, it should provide a very high gain, and as low noise amplifier, so the noise should be very low. So keeping these two things as a proactive one, I've designed my amplifier. So So wearable devices are found in many scenarios, but still in many applications, but still in medical application, it finds a vital role. So, for example, if when instead of any wired device or any thing that can be any devices that should be attached to the patient going to the hospital, from the remote place itself, using the wearable devices nowadays, they're capturing the data, details and analysis, which is being sent via any wireless network like Bluetooth or Wi-Fi to the receiver. So where this amplifier should be available in order to enhance the signal strength to analyze from the remote end. So that is the main purpose of these respective LNA. With respect to this medical body area network, I've designed this LNA to operate under the frequency range of 2.4 gigahertz. Apart from high gain and low noise figure, I've also achieved a good input and output matching, which is a very important property for a good LNA. Also, the stability of the LNA is found to be good. So basically, I've used a couple of CMOS transistors here to design my LNA. The software simulation I've done using the tool Advanced Design Software, ADS software tool. So these are all the performance parameters: amplifier gain, a noise figure, stability factor, and impedance matching. There are other parameters like linearity, power consumption are also there, but still I have designed in such a way it meets at least these specifications to the core. So I've talked about the wearable device already. So these kind of things like personalization, early diagnosis, mainly for remote patient monitoring and for information registry things. So in these areas and all, wearable devices are they are like a must use application. So and where this LNA is useful. So the existing system that I have taken is for wireless sensor network. The LNA, which is designed for a wearable wireless sensor network, which operates at the same body area network 2.4 gigahertz, where they are found to be the noise average as 3.3 decibels. So for an ideal LNA, it is good if the LNA has the noise figure to be 1, because as the name suggests, the noise figure is the very important character to be less than 1. At least it can be around 1, whereas the existing paper which I have taken, I'll show that in the reference paper list, it has given an average noise figure only, which is 3.3 decibels. So and also the gain is also 14.2 decibel, which is not a very great gain. So in order to overcome these noise figure and gain values, I have done some changes with respect to the topologies and configurations to achieve a high gain and low noise figure. And also here they have produced, the power consumption, the circuit was 30 microwatt. So coming into my proposed system, which here 2 MOSFETs were used. So instead of going for a coupled stage or a dual stage like that, I've designed in a way it is a cascode type of single stage one, because I, apart from noise, gain and all those things, I want the chip to be a very small in size, because as the size decreases, the power consumption, power dissipation will be reduced, and also as it is for wearable device, as the size decreases, it will be good for the device. So in thinking that, in keeping in that in mind, I have chosen the single stage cascode type of this inductive degeneration topology. I'll explain the topology details later. So I have achieved more than 20 decibels to be exactly say 20.09 dB with the noise figure almost it is 1 dB, so 1.03 decibels at this operating frequency. Also, my LNA have achieved a good matching, input and output matching, and also the stability factor I've calculated for the LNA, which proves to be a very stable one. So these are all the literature works I have gone through it. So this part, the first one, the design analysis of 2.4 gigahertz, 30 microwatts CMOS LNA, wearable WSM. This is my very base the main paper which I have taken. So here the way they have achieved a good power consumption was very less. That was the very big advantage of this paper. But still, the noise figure and the gain and all, as I said earlier, it was not that too much good. It was an average one. So, in order to overcome this poor noise figure, I worked on other LNAs also. So, gone through these kind of papers. Okay, so for various applications like X-band and for W-band application, wherever this wearable wireless techniques can be involved. So also using HEMT technology, I've analyzed some papers and the different CMOS technology, not just 180 nanometer, 65 nanometer, 45 nanometer, those kind of CMOSs I have analyzed. Where I could see.
Finish it quickly.
Yeah, sure. So these papers I've gone through it, and after which that I'll just explain this topologies in a short way. So many topologies were there, out of which these 5 topologies I've gone through it. So everywhere we found like noise figure. That seems to be the big issue. So again in series shunt feedback also, here noise figure is reduced but power dissipation has increased. So coming to the another topology, here again this is not suitable for narrow band amplifier, whereas my amplifier comes under narrow band frequency. So this seems to be the best one, inductive degeneration common source topology, where it has produced maximum power transfer and best impedance matching, as well as the noise figure is reduced considerably. So here, this is the exact design where a cascade of 2 CMOS, 180 nanometer CMOS has been used. So this one, the last one, the 4th one, which I have chosen because of these advantages. So these design equations I have used to found the RLC components values for the matching circuits and biasing circuits. This is the exact proposed LNA which I have designed. So this is the input matching, this one, so which is a 50 ohm. This is the output matching network, which is again matched to 50 ohms. And this both the CMOS are 180 nanometer CMOS, and which is of 360 micrometer length, and the MOSFET 2, which is 85 micrometer length. So I have simulated and found the output to be at 2.4 gigahertz. It has given 20.091 gain, which is very high. And the noise figure, my work has given a good, very high noise figure of minimum noise figure is 1.032, which is almost near to ideal one. Also, the minimum noise figure is 0.864. This should be less than 1, and I have achieved that as well. Coming to stability factor, it is 2.811. So as the value of K increases greater than 1, stability increases. So here the LNA proves to be a stable one as well. The other S parameters respect to the amplifier, I have achieved a good input return loss. So this reflection coefficient, output reflection coefficient, and reverse isolation and voltage gain, that is amplifier gain. So all these parameters, they have met the requirements of a good LNA. So comparing to the existing and other works which are for wearable devices network, my proposed work, which again use the 180 nanometers CMOS, achieved the more gain than in these papers. Also, the noise figure seems to be ideal one, almost near 1. So these are all my reference paper which I reference for this work. That's all. Thank you.
Thanks for the presentation, ma'am. I have got one question for you. Have you tried using Miller compensation in junction with this low noise amplifiers?
So I say I'm not getting you.
Okay. The thing is, you have used LNA. Along with LNA, if you would have tried for sub-amplifier Miller compensation techniques, that will further reduce the noise levels so that this type of devices can be used for neural imaging, something like that.
Okay, sir, because as I said, with respect to wearable devices application, I have gone through certain papers. So where they have been suggesting like this current reuse techniques And this cascode kind of inductive degeneration topologies, they were repeatedly used. So in that, I tried to sort out to be a single topology and reduce. So like I've aimed in that way and worked and produced it. But anyway, what you
Okay,
said, I will
ma'am.
take into considerations.
Just browse through some of this EEG head caps and smart sleep based devices.
Okay,
You
sir.
can get more inputs. That are recent wearable devices that come into the market to analyze the kind of neural signals.
Okay, sir. Sure, sir.
Thank you.
Thank you so much. Can I unshare my screen?
Yes, ma'am, please.
Thank you, sir.
Next paper is P00004. Vinod Kumar and Kamaya Rasi. Yes, ma'am. I'll just make you a co-host. You can unmute yourself and you can share your presentation. And then before starting, let me announce something. Those who have to give your presentation, and if you are present here, please write it in the chat box with your paper numbers so that I know that you are available and then make it available.
Shall I start, sir?
You can start, yes.
Good evening to one and all. I am Kalayasi from IETCCSD College of Engineering and I am guided by Mr. B. Vinod Kumar. I am a final year student doing Bachelor of Engineering. First of all, my project title is Reduction of Peak to Average Power Ratio of OFDM signal using threshold rotation method. That the main abstract is that to peak to average power distortion is reduced by using the threshold rotation technique, which can be found out after the function of IFFT, in which the signal is mixed with modulated discrete data of OFDM signal, which can before passing through the high power amplifier. The main benefit of the technique is to minimize the PAPR, that is peak to average power ratio. The main objective is to reduce the peak to average power ratio in OFDM system by using the threshold rotation method, which can use as a circular convolution method. First of all, OFDM is a orthogonal frequency division multiplexing, which is also called as multi-carrier modulation. Here, large number of closely spaced orthogonal subcarrier signals are used to carry data, which can split into several parallel data streams. This formula can denote a function of I50, which can convert into frequency domain signal to time domain signal. Next, this is a general OFDM block diagram. First of all, here QPSK modulation signal can be used. The random bits are generated in the input area. Then it can be modulates, that is, changes the signal into the convolution. Convolution can do the function as a multiplication process. IFFT can do the function as converting frequency domain signal into time domain signal. After the function of IFFT, we can add the cyclic prefix. Cyclic prefix are also called as God band signals, which can eliminate the inter-symbol interference. Next, the function of convolution is to the circular convolution. Here, the circular convolution can be used, which is also called a cyclic convolution, which is a special case of periodic convolution, which can compensate two periodic function that have the same period. By using the linear convolution, it is not more efficient. So we move to the circular convolution. Like the cyclic prefix. The cyclic prefix is also otherwise called as God interval, which is periodic extension, and it can be removes the intersymbol interference from the previous symbol. The main drawbacks of the OFDM system is the high peak to average power ratio, and there is a high computational complexity, and it's sensitive to frequency offset drift, carry drift. Then PAPR is a peak to average power ratio, which is a high, which can be defined as a maximum power divided by the average power, which can be found out the high intensity peak value after find out PAPR function as maximum power divided the average power. This is a general analysis of PAPR for general OFDM signal. This can show the peak power, that is maximum power. The tools used is MATLAB version 2010B. MATLAB can be used as a high-level programming language, which is more faster than the C, C++, and Fortran. It can be used in such applications as image processing, wireless communication, control design, etc. These are the problem statements in our presentation. That is lessening effectiveness of RF amplifiers and increase in bitter. There will be no linear distortion at the high power. The threshold method is one of the technique. The peak power distortion lessening scheme, which is dependent on the threshold rotation technique, is suggested to lessen
Your voice
the
is
peak
breaking.
to average power ratio at the weight of the character. A threshold weight is executed on separate OFDM signal.
Your voice is breaking. Can you hear me now?
Sir, clear.
Please unmute yourself.
A threshold weight is executed on separate OFDM signal via a certain kind of a band limited signal, and an OFDM signal can formed with a weighted discrete data and is then considered as a threshold rotation technique before passing through the high power radio amplifier. The process is repeated until it satisfies the condition to lessen the PAPR, that is a certain, until a certain range it can satisfy the condition to lessen the PAPR. The actual signal is completely recovered at the collector side. This is a block diagram of the proposed technique. Here the circular convolution can be used after the function of 550. The threshold technique is rotation technique will be continued until the range is occupied. This is the output of the existing and suggested method. Here the solid line can show the weighted OFDM method. Here it can be deviates and it can be exist at the 10 dB paper performance, and CCDF will be achieved as 10 to the power of -2. For the threshold rotation method, I have achieved after the 9 dB PAPR as 9 dB. Likewise, a PAPR reduction by using the 64 QAM. Here it is almost the same by using the QPSK and also 64 QAM. Here it can be deviates in the sense of 10 for the weighted OFDM method. For the threshold rotation method, it can be deviates in the 9.8 dB. This is a bit rate performance of the existing and suggested method. That the variation between the existing and the suggested method will be the 1 dB. The SNR rate will be 1 dB. The conclusion is that this analysis is only based on the taper reduction as well as a bit rate performance by using the threshold reduction method. The future expectation will be based on the power distortion of the OFDM risk transceiver implementing by using the WiMAX architecture. These are the reference which I refer. Thank you.
Okay, thank you. And when you process using this OFDMs, typically the sample timing, offset timing is not varied that much. It's quite less sensitive. So did you focus on that part in your work, or just the architecture and the flow you checked and SNR rate only you analyzed?
Yes, SNR rate and PAPR only analyzed, sir.
Okay, okay. These are some of the internal things inside OFDM that you can look on to improvise the performance. Okay.
Okay, sir.
Thank you.
Thank you, sir.
Any other questions, sir?
Not from my side.
No, sir. No questions. No further questions. Thank you then.
Thank you.
you. So, paper P005. Is someone present here? Can you just write it in the chat box if you are present? Just let me make you a co-host. So others whose papers are to be presented from P005 up to P012, please write it in the chat box, your paper number, so that we do not face such problems. So I've made you the co-host. You can unmute yourself. Priyadharshini, you can unmute yourself and you can share your PPT.
Sir, I think they have some technical.
Okay, in that case, we'll wait for you.
Next group, we can go for P006, Nandini
Yes,
and Ilavarasi, ma'am. Yeah.
this is P006.
Yeah, they have messaged, I guess, in the chat box.
I've made you a co-host. You can present your paper. You can share your PPT.
Good afternoon to everyone. Good afternoon to everyone. Good afternoon, everyone. My project is about landslide tracking using IoT sensors. I'm Nandini S. from IFT College of Engineering. Nowadays, we can see the natural disasters like landslides, avalanches, and floods are results in very heavy damage to the human, to the society, and also to other living things. So, in order to protect the people from landslide, I have developed my project. Introduction of my project is we already know what is meant by landslide. Landslide mostly occurs due to cutting down of trees or when a heavy vehicle move from one place to another of buildings and so on. These are the literature survey we have referred to develop my proposed project. First, landslide monitoring system implementing IoT using video camera. In this, the feasible and the efficiency is very less. So I have in this it is a major problem. And the most advantage of this project is by using the video camera, we can monitor the landslide. And next one is natural disaster monitoring and alert system using IoT for earthquake and landslide. In this, they have used the Bluetooth, but Bluetooth device can cover up to only 10 meters. So it is one of the disadvantages. And like this, we have go through mostly 5 to 6 papers. If in existing system, if we see means the most in all the project they are using wireless sensor networks and Bluetooth device to monitor the landslide and to intimate to the people. But the efficiency of wireless sensor and Bluetooth is very the accuracy level is very low. So in order to make it better efficient, I have developed my proposed system by using IoT sensors. In this system, in my proposed system, if you see means I have used 4 types of sensors: vibration sensors, temperature sensor, accelerometer sensor, and soil moisture sensor. By using these 4 types of sensors, we can send message to the people by using GSM, and also the location also will be sent to the people by using GPRS. At the time when the network is lost means at the time we are using buzzer, so it can alert the people simultaneously, so the people can be moved to the safer place. It is my system architecture. We are using the microcontrollers Arduino Uno, and we are using the temperature sensor, vibration sensor, soil moisture sensor, and accelerometer sensor. These 4 sensors will be placed in the soil. So when the it will calculate the temperature as well as vibration and the moisture content and the speed or level of the vibration. So when it exits range, it automatically sends a message to the GSM as well as to the GPRS and buzzer. It will send to the message to the rescue team and also the people who are living around the areas, so that the people can be moved to the safer place. In my project, these are the modules I have used. Sensing unit. It is used to sensor data through sensors, and it will be data will be sent to the users, sent to the control unit, and the control unit will control all the components in the system. In tracking unit, we are using the GPS to locate the area, and communication unit will send the message to the people about the landslide. The modules are split into 4 parts. This is the overall view of it. And my working model of for landslide project, this which I used to detect the landslide. And this is how the output will be provided. In this, all the ranges will be displayed, and you can see there is a link below. If you click this means it will show where the people can be moved to the safer place. It will be shown like this. So that the people can be moved to the safer place simultaneously. My advantages of my proposed system is to develop a monitoring system in order to create awareness among the people, and it will also intimate about the people before the landslide is going to happen, so it can save a human life as well as the economic level of country. These are the references I have used for my project.
Thank you. Any questions?
Yes, sir.
I'm asking the people here. So, how do you think the GPS will be a better than the Bluetooth or the Wi-Fi? I'm not sure.
Okay, sir. One quick question here, sir.
Yes.
Yes, sir.
With regard to
Yes,
the
sir.
communication methodologies used, what type of technology did you use in this project, ma'am?
We are using GSM to send the message to the people, sir.
Through Wi-Fi you are doing it? Or how does it communicate?
By using IoT concept only, we have developed this project, sir.
IoT controller will get the data from the sensors. It has the data with it. Then how does it transmit?
How will the people around the area
It will
know
transmit.
about it?
I'm not able. What you're saying?
You said that once this system detects some function, then you will transmit the communication to the people living in that particular area, right?
Yes, sir. Sir.
So how will they come to know? So how will you communicate with the people, or because there should be some
by sending message. By sending message to the people, sir, that I have shown here. Like this, message will be sent to the people who are living around that area, sir, and also to the rescue team. So when people did not get alert at the time, the rescue people can come and save their lives, sir.
Any other questions? Okay, that is, thank you.
Thank you, sir.
P005, did your technical problems improve? Problem? So you can present it now. Yeah, okay. Just give me a minute. I'll make you a co-host, and then you can share your PPT. You can unmute yourself. You can share your screen.
Good afternoon, everyone. Sorry for the inconvenience and thank you for the opportunity today. Am I audible, sir?
Yes, yes.
Okay, we are a team from MEPCO Engineering College, Sivagasi. Our topic is damage detection in aerospace structures using the optical fiber. So our topic is generally an abbreviation. I would like to elaborate on the topic first. So the damage we are going to address here is the damage caused in the aerospace structures due to the bird strikes. Though the bird strikes may seem insignificant compared to the size of the aircraft, they cause many fatal accidents, which has caused the damage worth of $400 million, and it has almost killed 210 people. So it is an important issue in the field of aviation industry. We have taken into consideration that damage, and the aerospace structure we are going to concentrate is that the wing structure of the aircraft. So the wing structure is the main part which is more vulnerable to the bird strikes. 33% of the bird strikes are happened in the wing region of the aircraft. To be more particular, the wing leading edge is the part we have taken into consideration in our project. So the optical fiber we have used is the CFBG sensor, which will be placed inside the optical fiber. CFBG sensor is the chipped fiber Bragg rating sensor, which is designed using the optic rating software with the following specifications. So these are the specifications with which we have designed our CFBG sensor. The CFBG sensor is designed based on both the strain and the temperature. So it is essential to eliminate the temperature coefficient in our application because the CFBG is used to detect the damage caused by the impact forces of the bird strikes causing the strain. So this is the aviation safety data which is obtained from the ATSB, which is the Australian Transport Safety Bureau. It is a major aviation corporation in the field of aircrafts. So the first three columns indicate the values which are taken from the ATSB. We have converted the values into Newton. The impact forces which are in tons are converted into Newton. So this conversion and the microstrain is calculated by using the softwares. In console, this impact force, that is the third column, the impact force which are given in tons are converted into Newton. They are given into the software called the console, where they are used to find the corresponding strain which are produced in the aircraft. So this is the corresponding microstrain. The last column is the corresponding microstrain which we have got using the console multiphysics software. So the tensile strength is also a parameter which we have used to detect the damage occurrence in the aircraft. So initially, our project is used during the manufacturing process of the wings as a testing procedure in the simulator environment. So we can produce the aircraft wing structures which are more sustainable to the bird strikes in the real environment. So this project can also be extended to be used as an alarm system in case of the real-time experiences of the bird strikes. So this is the wing structure we have designed using the SolidWorks. And the rest will be explained by my teammate Akshya. I hope she is online. Akshya, are you online? I think there is a problem with her still. So I would like to explain the remaining part. These are the reflection spectrums we have obtained using the CFPG sensor, which we have designed. So these are the reflection spectrums.
Ma'am, please put in presentation form.
Okay.
Slideshow. Yeah.
So this is our main procedure. We have designed the CFBG sensor using the optic rating 4 software, and we have designed the aircraft wing structure using the SolidWorks software, And the simulation of the strain analysis model is done using the COMSOL Multiphysics 5.3a software. So based on all the simulation works of combined of these three softwares, we have detected the damage in the wing structures. In the already existing papers, they have used the FBG sensor. In our project, we have used CFBG sensor. So that is the improvement we have done. We'll be placing the fiber in the form of the zigzag pattern in order to cover the full area of the aircraft. So these are the basic settings we have used in the COMSOL Multiphysics software. This is the wavelength shift for the strain obtained for the 8 cases of the fiber. The 8 cases are those which we have shown in the aviation safety data. So we'll be applying the values we have obtained using the Newton. This Newton will be applied and the corresponding micro strain will be found. So we have used these 8 values to create these graphs. So we'll be first producing the Newton and the corresponding strain will be found out using this graph. So these are the 8 cases. And these are the 4 cases which are based on the fiber which is placed on the leading edge. Those 8 cases are those for the fiber which are placed in the zigzag pattern. So this case, this is the first case where the bird strikes on the first 100 meter of the leading edge. And this one is for 100 to 200 meter. And this one is for 200 to 300 meter. And this is for 300 to 400 meter of the leading edge. So as I have said earlier, the CFBG sensor is based on both the strain and the temperature. So it is essential to eliminate the temperature coefficient. Because in our experiment, only CFBG is used to detect the damage caused by the strain. This is the temperature-based shift we have designed. This is how we have cancelled the temperature effect. This is the wavelength we have got for the Newton. So as I have stated earlier, the extended application can be used as an alarm system to alert the pilots to learn on the nearest safety data. So these are our references. Thank you. Do you have any questions?
Thank you. Do you have any questions?
Excuse me, my batchmate wants to tell her points. So can I connect on her phone? She is not able to join using the Zoom meeting. Is there any chance?
Try. I'm not sure whether it was of noise issues. Can have a try.
Sir, sorry, I'm not able to hear your voice properly.
Is she with you, ma'am? Is she with you?
No, she is in other place, but she wants to contribute to this. So she wanted me to connect me through her phone.
I didn't catch you, ma'am. What she wants?
She has called me now, so she wants me to connect this call to this meeting so she can tell her points.
Connect this call means through phone.
Yes, ma'am.
Yeah, you try, ma'am. Try.
Thank you. ஸ்டார்ட் ஆயிடுச்சு. நான் அது பேச முடிச்சுட்டேன். நான் கனெக்ட் பண்ண சொல்லியிருக்காங்க. நான் ஸ்பீக்கர்ல போடுறேன் பேசுறேன். Okay. Excuse me, ma'am. She is connected. She'll speak now.
Okay. Ask her to continue.
Akshay, you can speak now.
This is the design specification of our fiber, and we have designed 2 fibers. One fiber is to be kept below the skin of the wing, and the other is on the leading edge. The length of the fiber is about 400 meters, and the expression for the linear variation in the waiting period of the fiber is inbuilt in the optigrating software, and the reflection spectrum response curve is of 4th order Gaussian curve. And in this curve, we have for fiber 1 we have kept U as constant, And for fiber 2, we have varied the U value so that the width of the gratings is varied. And in the fiber 2, there are, as I said, 4 gratings, and each grating, the U is varied in order to vary the width of the Gaussian curve. This is done in order to localize the damage. And this is the next, we go for the wing structure. The wing structure is, the type of the wing structure is airfoil, and the span of the leading edge is 540 meters, and the span of the wing root is 150 meters. The material we have incorporated is 7075 T6 aluminum alloy. And next we go for the wavelength shift of the corresponding impact forces. Here we have simulated the strain analysis using the COMSOL multiphysics software, and the corresponding wavelength shift is observed in the operating software. Here we have 8 cases. For each case is for impact force, and this is according to the aviation safety data that is previously explained. And next, the wing root is fixed constraint here, and the force is applied on the leading edge to obtain the strain responses. In the left side, you can see the strain responses that is obtained in COMSOL software, and in the right side, you can see the corresponding wavelength shift. For the first case, you can see there is 126 ppm. Similarly, for the 8 other cases, the corresponding wavelength shift is denoted in the right side graph. The next we go for the fiber 2. In fiber 2, we have 4 cases. As I said, the width of the gratings of the four fibers is 4 fiber grating is varied. So therefore, we can identify in which part the damage has occurred. So in order to show that variation, you can see there are 4 cases. For first 100, if the damage is occurring in the first 100 meters, then you can see the particular grating is being shifted. Similarly, for 4 other cases, you can see there is variation in the width of the curve, so that we can easily localize the damage. And next, we can see the temperature variation. As optical fiber is usually depending on both the strain and temperature, it is necessary to cancel the temperature effect. So we are doing this process. Here only the shift for the temperature of the temperature decrease of 6.5 degrees Celsius in the troposphere is happening for every 1 kilometer. So the particular shift for the decrease in temperature is denoted, and this shift is multiplied with the height at which the aircraft is flying, so that we can subtract this total shift from the shift that is shown in the spectrum, so that we can obtain the real wavelength shift that is happening because of the strain effects. And then we go for the tensile strength based damage detection. In the tensile strength based damage detection, the tensile strength of the aircraft wing is 503 megapascals, and this is used as the threshold limit. Beyond this limit, there is obvious nature of the wing to get damaged. Therefore, the corresponding wavelength shift for this particular tensile strength is calculated, and this is kept at the threshold wavelength limit. Beyond this wavelength shift, there will obviously be a damage, and this concept can be extended for the application of alert system. So in case if there is a damage in the aircraft wing, then the pilot can be alerted, and he can land it in a nearby safe spot, so that major accidents can be avoided.
So thank you. That was our project.
Thank you. Have any questions, ma'am?
I think no, sir. Because the
I
area
had one question based on the temperature, since
Hi, sir.
different aircrafts will fly at different, or the same aircraft can fly at different heights, and hence the temperature can vary. Right? As you said, it's 6.5 degrees per kilometer.
Yes, sir.
Temperatures at different heights will vary.
Sir, our application is mainly to detect the damages based on the strain measurements. So we cannot totally neglect the temperature. So we have considered that into account, and by that considering it as a common factor, we have a constant value, we have subtracted that from.
So that is what for different heights the temperature will vary differently. So how can you?
Sir,
Just by
mostly the
returning
flights
a
will be
constant value,
flying on
how
the
do you think
troposphere
that,
surface.
Sorry?
Hello. Hello.
Yeah, can you please repeat?
1 minute. Sir, most of the flights will be flying in the troposphere, the part of the atmosphere which is troposphere, which is the lowermost layer. So in that, we have considered the temperature factor and we have eliminated that.
Okay, thank you.
Thank you. Sorry for all the inconvenience, sir.
Okay.
Thank you.
Yes, sir.
Yes, ma'am.
Shall we go to the next one, sir?
Yes, ma'am. The next paper, she mailed me that they have asked for a time change in slot.
Yes, yes. Paper 7 has asked for time change.
Yes.
Paper 8 we have to take, sir.
Yeah, paper 8. Is someone present? Just wait, I'll make you the co-host so that you can share the you can unmute yourself and share your presentation.
She's Deepa J.
Deepa J. Please unmute yourself. Share your presentation.
Deepa J. She has some technical issues.
Maybe we can go on to the next one and then.
Yeah, sir.
Okay, so we'll wait for your issues to get sorted out. Meanwhile, we'll move on to the next paper, P009. Is anyone present?
P09, Kartika.
Please write it in the chat box so that I can know who is.
Kartika, Lalita Bharati, Dinesh Kumar. Anyone Kartika, Lalita Bharati and Dinesh Kumar? Paper 9.
I think no one is there or some connectivity issues.
I think is the time is 4:45. I think they may not log in maybe. Deepa, are you ready? Deepa?
Okay.
Yeah.
Hey, ma'am, I'm making it the host as well. That you can also ask the permission. Hey, ma'am, I think Deepa Ji is ready.
Hello?
Ma'am, I think Deepa Ji is ready for P008.
Yes, sir. Yes, sir. We can ask her to present, sir.
I made you the host.
Sir?
I made you a host, ma'am. Make them the co-host.
No, sir. You can continue, sir. No issues. You can continue.
Actually, there's some issues, technical issues I am also facing. That's why I made this one. We can make me the host again so that I can add her.
Sir, okay, sir. You made me co-host, sir. Just I made you host now.
Yeah, I'll just. Jay, I've made you the co-host.
Yeah, sir. Yeah.
Now you can unmute yourself and share your presentation.
Yes, sir.
I made you a co-host.
Okay, sir. Thanks, sir.
So made Deepa J the co-host as well.
Yeah, she started her screening.
You can unmute yourself and then
No, sure.
presentation.
Open the presentation and start.
Good evening. Audible, sir?
I think there's some technical issues.
Hello?
I think there's some technical issue again. So
Yeah,
we've lost the connectivity. P009, anyone present? Kartika, Lalita Bharti, Dinesh Kumar. P1 to P010?
010. Anyone from 010?
010.
Akshaya, Suchitra, Irshad, Narasimham, Vaibhav. I think Akshaya is the first author. Akshaya. Is Akshaya available?
Yeah.
Yes.
Yes, ma'am, I'm here.
Akshaya, can you give, are you ready? Can you give presentation?
Yes, ma'am, I can give.
Yeah.
Is the screen visible?
Yes. Please make it in a slideshow mode.
Okay. Is it visible?
Yes.
Good evening, one and all. I am JB Akshaya from VVC Mysore. It is my privilege to be giving this PPT on review on fractional and frequency synthesizers on behalf of my team. First of all, a frequency synthesizer forms an integral part of an RF or microwave industry. Delivering them in terms of small size, high performance, low power consumption, and low cost is very important. As we are aware, a frequency synthesizer forms an integral part of any radio any radio. So the main reason why I did this study was because for a final year project, which is designing a fractional synthesizer for a software defined radio. So we did an elaborate study on various technologies currently being used, and these were our findings. First of all, we started with a programmable PLL, which was the first available frequency synthesizer. So in this, the overall frequency division, etc., which is required for radio tuning purposes, was done by means of a DSP processor. When we tried to physical design for this, there was a problem in area and power, because a DSP uses a lot of power and also it occupies a huge area. So, and also noise could not be controlled by this method. Then next, we moved on to FCMW chirp generators. This is chirp generators are nothing but impulses, like, basically. So this deals with analog technology more than digital. But we studied this because of mainly power. Like we could reduce we could reduce power, but again, there was some problem with bandwidth. And this process was easier to implement in our strategy, because when we are dealing with high frequency, chirp generators are proven to be the best. Another similar study on this showed that the phase spectrum had an adverse effect on FCMW chirp generators range resolution. And also the phase noise and frequency errors were minimized by adopting the charge pump current and loop filter capacitance for ramp slope. Then we studied various methods to reduce spurs. Spurs are nothing but noises and abrupt changes in the input signal. So as we know, a frequency synthesizer consists of a voltage controlled oscillator as the first block. Then we have a frequency divider and then a phase detector. So usually there is only single VCO involved. But then this study showed that when we have multiple VCO, like, 2 VCOs, and two charge pumps respectively for them, then there could be a way to reduce the noise. This study was done. And also the spurs mainly arise due to the nonlinear phase detector and high gain of voltage control oscillator. Since we are using two voltage control oscillators, the gain could be controlled, and also for the problem of nonlinear phase detector, phase adjusting was done. Also, we could use BiCMOS technology to reduce the noise further. And this is more effective than the sigma delta modulators, which are currently being used in many synthesizers. Then we have field programmable gate array based concept. For a VLSI physical design, there are basically three styles to design them. One is the standard layout, standard cell layout. Another is fully designed layout, and another one is a field programmable gate array based logic. Though this is quite outdated and used for small circuits, this could also be implemented in designing an ideal frequency synthesizer. In this FPGA model, we studied about quadrature direct digital frequency synthesizer, which could rapidly hop between the fractional frequencies. This was a very fast approach, like we could get the output really faster. But again, the problem was with the area. Like as we know, field FPGAs occupy more area than a standard cell layout or full custom layout. Then next we studied injection locked frequency dividers. In this case, the whole design was divided into high frequency blocks or low frequency blocks. The low frequency blocks included the divider and VCO. This whole thing could be replaced by spiral inductors on chip. So this reduced the area greatly. But the problem was with the speed. So we could use the previous FPGA model and increase the speed. But again, to reduce the area, injection locked architecture could be followed. High frequency CMOS fractional and frequency divider, as the name itself says, it is for high frequency applications, beyond 3 gigahertz. When we're talking about high frequency, this model in which we use prescaler control and divide the ratios as n and n plus 1, it could help a great deal. Flying adder based digital frequency synthesizer. This is used mainly due to the simplicity and effectiveness. The design is pretty simple to understand, but again, the problem was they had done it in 0.18 micrometer or 180 nanometer technology, which is quite outdated right now. Like when we can do a better design with 45 nanometer technology, we thought this was pretty outdated, but then again, the challenge we took up was to design this in 45 nanometer technology. Design of high accuracy synthesizer. So again, our frequency divider, we wanted to make it accurate with less possible jitters. So we studied this technique in which they have used a sigma delta modulator to control the prescaler. And this is accurate than a decimal frequency divider. Like there's another concept called decimal frequency divider. A fractional frequency is anytime better than the decimal due to the precision value. Hence, we took up this too. Dual VCO, as I had discussed in various methods to reduce spurs, this helped a great deal. When a VCO is divided into two, its overall gain could be controlled, and also by adjusting the phases of the phase detectors, we could divide the frequencies more effectively. 45 nanometer PLL, one such design was done so far in a 45 nanometer technology, but they have not used injection based architecture or the flying adder principle. Our aim was to design those in 45 nanometer PLL. So we studied this as well. 90 nanometer CMOS, this is also currently available. They have implemented using logic gates. This is more of a digital concept using XOR gates, D flip-flops, etc. And they had designed this architecture for 800 megahertz fractional value. And the results were quite impressive. 180 nanometer, as I've discussed before, I guess we can skip this. A power efficient PLL frequency synthesizer. This is one major important aspect when we are designing a frequency synthesizer. Since we are operating on high frequencies, power has to be a great importance here. So in this architecture, which was done in a BiCMOS technology, they have reduced the phase noise with power efficiency. So here the Colpit oscillator was used to increase the gain, varactor gain, and for post-tuning of the frequency. From the above research papers, we have observed the following. The first method to design a fractional frequency synthesizer was by writing behavioral description. This could be done in Verilog and VHDL, but this method had a problem with the spurs, that is the errors. Then the spurs could be controlled to an extent using injection lock frequency dividers. And also to make the model simple and achieve in a greater speed, we use flying adder principle. However, we have also found out that there is considerable amount of problems in converting the continuous time signals to discrete time signals. This problem occurred because there was absence of sampler block in the design. And so again, to cover this gap, we are planning to incorporate ADC block, and that is analog to digital converter, using 45 nanometer technology, and we can give better power results. Conclusion. So there's an increasing demand for frequency synthesizer with day-to-day advances in the field of microwave and radio technology. As I discussed previously, an efficient design with injection locked and flying adder principle could give a better synthesizer than which is available in the market for a specific application. In our case, for software-defined radio, we can make a better application. Thank you.
Ma'am, have you implemented any circuit in here?
We were currently working on it, ma'am, like for our final year project.
Okay.
And so we have kind of done it like to the nth level, but right now, because of the pandemic, we are not able to go there and get the reports which are necessary.
No. Can you, like, your presentation is moreover like a literature review, right?
Yes, ma'am. It's a review paper.
Okay. No. Just while you're explaining, you're saying we have the last slides that you have implemented. That's why I have a doubt.
Yes, ma'am. The doubt in the sense?
Okay. And you mentioned about FPGA, semi-custom, full custom, like that. So can you differentiate them clearly, ma'am? Can you differentiate?
The difference between the styles, is it?
Can you differentiate full custom, semi-custom?
Yes, ma'am, I can. Okay, so in a full custom design, it is when we design the standard cells also required for the physical design. Like for physical design, we do all these processes of placement, routing, connection, verifying the connections, etc. So for the fabrication process, when we are doing the design, full custom layout includes designing using the standard cells which were also done by us. Whereas in standard cell layout, we can use this GPDK libraries, etc. available in the software, which we have used is Cadence. So the Cadence available libraries could be invoked in standard cell layout. And in FPGA, it is by making use of that FPGA processors.
Sir, are you satisfied with the answer?
Yeah, ma'am, somewhat.
Yeah, but still, I think some clarity is missing. Okay. And then you mentioned about dual voltage VCO, right?
Yes, ma'am. Dual voltage control oscillators.
Yeah. Dual voltage control oscillator.
Yes, ma'am.
Like how it is different from single VCO?
Single VCO, actually, ma'am, when we tried the simulation, a single VCO had a more gain than the double VCO. Like when we use two VCOs, the load could be reduced from a single VCO. And that made the process faster. And at the same time, power consumption was low because the runtime was reduced.
Any difference in voltage to frequency conversion ratio?
Conversion ratio, we didn't check on that factor, ma'am. But once the time is reduced, the power consumption automatically reduced. So we use dual VCO and also multi-modulus VCOs also we have tried. But again, when we incorporated more VCOs, the problem was with area. So to compensate for area, we reduced the number of VCO. So we stuck to dual VCO model.
Okay.
Yes. Thank you.
Thank you.
Yeah. We once again call Deepa, sir. Deepa Jain.
Yeah, yes, ma'am. You can call Deepa once more if she is ready. Yeah, okay. So,
Hello. Deepa Jain, are you there?
Deepa Ji, yeah.
Yeah, she's ready.
Good evening to all.
Are you giving with your mobile, ma'am?
Hello.
Are you giving presentation with your mobile?
Yes, ma'am.
Okay.
Sorry for my inconvenience. Myself, J. Deepa, Department of Information and Technology from IFT College of Engineering, Viluppuram. My project title is Cell-Powered Cardiac Pacemaker using OSI-4 algorithm. This device uses electrical pulses to prompt the heart to beat at a normal rate. In introduction, that can of the help control and monitor the heart. And pains controls that records a heartbeat, and efficient medical services can be provided to the patient in correct time. In abstract, in proposed system to design a failure-safe, responsive cardiac pacemaker device. Aging or heart diseases damages your sinus node's ability to for your heartbeat. Once that regulates your heartbeat and monitor the heartbeat when necessary. In literature survey, and first one, an effective sandwiched wireless power transfer system for charging implantable cardiac pacemaker device.
The font is not visible, actually, not clearly visible.
Can you make it in rotate the screen and then maybe?
I think you can, yeah, yes.
First one, system for charging implantable cardiac pacemaker that can use a wireless power transfer to battery or micro medical robotics for quad pacemaker. That plays a major issue is video sensors are expensive and sensor generate a huge data at a time. Next one, robust wireless power sensor use circuit that made it random non-radiative transfer, which require magnetic field coupling in the near field that required a expensive battery. And third one, circuit that can use both near field and far field wireless power transfer system. This is a fast growing interest in wireless power transfer.
Again, some problem.
Again, there is a problem.
Well, maybe just
Yeah,
should we
Padmash.
wait or should we go ahead?
Hello, sir.
Should we wait or should we go ahead? The next one.
Just we'll wait for 2 to 3 minutes, sir, for her.
Okay.
Is she logged out or?
I think there's some connection issues and that is why it is.
Yeah. Better we can call the other person.
P011 Padmasree.
Yeah, Padmasree.
Don't think she is here. P012 Nima Roslin, Sangeeta.
P011, P011 and P012. Anyone available?
You're there, just
P012.
P012. Okay.
P012 available, sir.
Yes, ma'am.
Sangeeta is available.
I made you the co-host. And present your PPT.
Good evening, everyone.
Yeah, good evening.
My name is Sangeeta. I'm a computer science student of IETCCSD College of Engineering. Today, I'm going to present about my paper, Women's Safety Android Application with Hardware Device. First, I'm going to tell why we need women's safety device and what this is all about. In our country, even though it has superpower and an economic development, but still, there are many crimes against women. The atrocities against the women can be brought to an end with the help of our device. This is the overall abstract of my proposed system. An advanced mobile phone can be utilized proficiently for individual security or different other assurance purposes, particularly for women. Our gadget is a security framework and Android application uncommonly intended for women in distress. We found an across the broad security gadget which has all the highlights in one click. We utilize the ARM controller and Android application in which both the gadget and the advanced mobile phones are synchronized. Introduction. It is easy to use application can be gotten to by any individual who has introduced it in their advanced cells just as who has our gadget. We will probably furnish you with the quickest and most straightforward approach to contact your nearby contacts. The fundamental methodology is to scan the moment area and the troubling a message to the cops and the preset numbers with the goal that terrible episode can be turned away and give continuous proof to the activity against the culprits of wrongdoing against women. Existing system. All the existing device must be connected to the GPRS service to work properly. There is a variety of applications for women protection when they are in dangerous situation. The disadvantage of using these applications are they are only send alert messages to the saved contacts. Because of previous system, there is less possibilities of overcome the dangerous situations of women. Previous applications also have GPS tracking system for to track the woman location, but it has not specific range. Existing system don't have the feature that don't send the alert message to nearby cell phone. In existing system, monitoring was tedious and mischance in arriving rate. This is the methodology of my proposed system. I developed Android application and a hardware device. First, I explain internal working of Android application. When we click start, audio will be recorded, SMS will be sent, video will be recorded, and camera is detected, which helps for police department. Next, internal working of hardware device. It has emergency button and multi-hidden camera. When single click, GPS is tracked, location is added to the template, and SMS sends to the preset context. Double click, audio record activated, record audio and sends SMS. When long press, it calls to the preset context and police department. It also contains multi-hidden camera. It is triggered by click on button, camera is detected and helpful for parents and police department. These are the technologies I used in my proposed system. GSM model to send the SOS message and call. GPS can track our present area. LCD can display contact numbers and messages. Sound recorders can record audio. This is my proposed architecture, which has both Android application and hardware device. This is the clicking button that I have explained in the internal working. LCD can display the preset context and shows the message also. An Android application dashboard contains start and stop button. You can understand why stop button is used by seeing results. This is the simulation result of my proposed system. It can send both SMS and email at same time. By clicking start, it sends location and also it detects current battery percentage. When we wrongly start the button, we can also stop it. It says, sorry, that was a false alarm. I'm not in any kind of trouble. Please ignore the previous SMS messages that you received from me. Advantages of my proposed system. It is all-in-one security system and no need to carry multiple devices. It records audio, can be also used for further investigation. It is most helpful for police department. When battery is running low, it can also send location to the preset context. My gadget can also works without internet connection. GPS can track the user live move and multi-hidden camera can detect the hidden cam. Multi-hidden camera can detect video. Conclusion. Our primary goal of this project is to ensure every woman in our society to feel safe and secure. We can send our location to our relatives and police department by clicking the catch. Providing women a safe environment in all situations, for example, detecting hidden camera, physical threat, harassed, robbery, stalk. With further research and innovation, this project can be used as a small wearable device like watch, pendant, etc. These are the reference paper I referred for my paper. Women's safety isn't expensive, it is priceless. Thank you for your attention.
Your objective is good. and your presentation, you mentioned more about the features rather than technical details, what I feel. You repeatedly mentioned about features of your project, but not the technical details. Can you go a little bit deep to the technical details?
For hardware device,
Yeah.
I used ARM controller and Bluetooth.
Yeah, just go to that slide which is consisting of hardware details. Yeah. Next slide. So which processor you have used? Hello?
Hello, ma'am.
Yeah. Speak about the technical details of your project.
I used GSM module.
Okay.
GPS.
Huh?
Then sound audio. Bluetooth.
Communication protocol?
Ma'am?
How do you communicate it through the, so you have already also made an Android application, right?
Yes, ma'am. Yes, sir.
So how do you communicate with the hardware system to the application?
It send SMS to preset context, sir.
Only when you press the start or stop in the Android application will it send it, right? Or what is it? How do you connect the hardware with the software?
Interfacing between the hardware and software.
Sir, I inserted a SIM here, sir.
Okay.
This SIM can, by using that SIM, we find we track the location, sir.
No, that is fine. I mean, the hardware will detect whether you are safe or not, right? If
In hardware, it in LCD display it shows preset numbers and it send SMS.
Which processor you use? Processor.
Yes, ma'am.
Pentium processor, ma'am.
Pentium processor. I think you have used ARM.
Yes, ma'am. For hardware, I used ARM controller, ma'am.
Okay.
To connect with hardware to Android application, I used Pentium 4 processor, ma'am.
Mm-hmm.
Any further questions?
Yeah.
Any further questions or?
Yeah, sir, we can conclude.
Okay. Thank you.
Thank you, ma'am. Thank you, sir.
And the seventh paper has just arrived.
Yeah.
Ask her to do it.
Yeah. Rishma?
Uh,
Yes, Rishma is available. I think you made her co-host.
yeah.
Yeah.
Good evening, one and all. Myself, Rishma from Bangalore. So my topic is power generation from the wasted energy of the moving
Voice is
vehicle
low.
using
Voice is
speed
low.
breakers. My topic is power generation from the wasted energy of moving vehicles using speed breakers. So these are the topics what I'm going to discuss. Introduction, analytical comparison, constructional details, block diagram, practical setup, and the results. So we all know that energy is a primary need for survival of all organisms in the universe. In this fast-moving world, population is increasing day by day, and conventional energy sources are reducing. The extensive usage of energy has resulted in energy crisis over the years. Therefore, it is necessary to overcome the problems. We have implemented a technique of optimal utilization of conventional sources for conservation of energy. Our design mainly focus on how to utilize energy which is wasted when the vehicle passes through the speed breakers. So electricity can be generated using vehicle weight and speed as the input. So kinetic energy of the moving vehicle will be converted into mechanical energy. This mechanical energy can be further converted into electrical energy by using a generator, and this can be saved by using a battery. And further, we could use it for a smaller domestic applications like streeting the lamps, etc. So there are many previously existing methods like crankshaft mechanism, roller mechanism, rack and pinion mechanism, air piston mechanism. So when coming to the crankshaft mechanism, so in the crankshaft mechanism, we are generating electricity by vertical movement, where the vertical movement is converted to rotational movement. Due to the heavy weight vibrations, the balancing problem of the crankshaft mechanism caused dash to the bearing used in the mechanism. When coming to the second mechanism, that is the roller mechanism, roller is installed by using some grip in a speed breaker. So when a vehicle passes over the speed breaker, it rotates the roller, and the movement of the roller is used to generate the electricity. The third mechanism is rack and pinion mechanism, where it is one of the famous mechanism. So kinetic energy is converted into electrical energy when it moves on the speed breaker. The rack will be pushed down. This rack is connected to the pinion. The motion of the pinion will be a reason for generating electricity. When coming to the last mechanism, that is air piston mechanism. That is when vehicle passes over the speed breaker, the piston of the pump goes down and air will be compressed. This compressed air has some velocity and can be used to rotate the turbine. So we have made a comparison of the different speed breaker mechanism in terms of cost, mechanism, maintenance, efficiency, and design. So what we have designed is bicycle pedal mechanism, and we have compared with the roller mechanism and air piston mechanism. So in case of bicycle mechanism, we are comparing with costs. It is moderate. Mechanical setup, it is bit little difficult. Coming to the maintenance part, it require maintenance on a weekly basis, as it depends upon the weight sustaining capacity. Next is about the constructional details. So here basically we have three systems, that is damper system, the second one is motion conversion system, the third one is energy system. When coming to the damper system it is required to support the speed breakers. Damper system, it consists of a spring which is required to push the speed breaker upwards when it is acted upon by the weight of the wheel. The next part is the motion conversion system. So here this system is required to convert the basic vertical reciprocating motion of the damper system into the rotary motion of the shaft. For this we use bicycle pedal mechanism. The vehicle load acted upon the speed breaker is transmitted to the bicycle arrangement. This vertical motion, it is converted to a rotary motion and it is transmitted to a sprocket arrangement. So as we see in the figure, we have two sprockets. One is larger sprocket, the other one is smaller sprockets. These sprockets, it is interconnected by a chain drive. Small sprocket, it consists of a ball and a ratchet which avoids the rotation in reverse direction of the shaft. Therefore, it will be a unilateral rotation. And also we have flywheel which is mounted to adjust fluctuation. The next is the energy conversion system. The mechanical energy that is available at the smaller gear, it will be converted into electrical energy by means of a dynamo or a generator. Next is block diagram. Breaker, it is transmitted bicycle pedal arrangement to spring that is mounted on the system, where the weight creates the force of the spring. The next part is the sprocket part. As I told, it consists of two sprockets. One is the larger one, the other one is the smaller in the diameter. Once the EMF that is produced, that could be stored in a rechargeable battery and that could be further used for any small applications. So this is practical setup of a design. So it is made up of mild steel and it is square in shape. The dimensions, it is millimeter width, we have chosen a 610 millimeter, and height it is 60.5 centimeter. System consists of one hump and it is made up of metal rods of 1 centimeter thickness. The angular joint by means of welding. The dimension of the is 20 height and 28 centimeter width. The bicycle pedal, it is connected to the ump as shown in the setup. The up and down motion of ump is caused by mechanical spring. The bicycle pedal is below the speed breaker and other parts are attached to the model by means of bearings and the overall the structure, it can withstand a load up to 80 kg. So coming to the results and discussion, we have assumed the mass of the vehicle as 10 kg. So we calculate the power. We for 24 hours we get around 387.36 watts, and for 60 minutes it is 16.14 watts.
Okay, Rishma,
Yes, ma'am,
how do you implement the prototype of this project? Hello?
Hello, one second.
Yeah. How do you implement the prototype of this project? Can you go to that?
This is the prototype we implemented. The top one we can see here, this represents the breaker.
So is it set up by you? Or
it is set up by a batch of 4 students.
Huh?
It is set up by, it is set up in our college only.
Oh, yeah. Okay. Fine.
Oh.
Okay. Yeah, you can conclude.
Conventional energy sources have played a significant role in the power generator sector. So in this project, we have developed a model wherein we can generate small amounts of power for local lighting the street lamp, etc. So this provides an affordable solution for energy crisis to the common people. India being a developing country, energy management is prime concern for most of us. By using system, one can drive vehicles load, whichever the kinetic energy, whatever it is wasted, it be used for a useful way. So many such units, it could be implemented in highly populated areas near the toll booths and used for practical applications. These are the references what I have referred.
Okay.
Thank you.
Okay, fine.
Thank you. I had one question regarding the maximum weight that the prototype that you have developed was around
Okay.
80 kgs, right?
Yeah, it could stand very.
So generally the vehicles will be having a much higher weight. So how do you?
So they have to increase the capacity by choosing a steel which can withstand weight for higher weight. Since it is a practical, it is prototype, we have used this dimension.
So have you given it a thought about how can you implement for the larger weighted vehicles as such in general?
Same model could be used if we want to develop more power. The number of rotations that should be increased. Then we can generate more power when compared to the prototype.
No.
Okay.
Yeah.
Thank you.
Yeah, yes, sir. Sir, I think P9 is available, sir. P9, P9. Kartika, I think she's available.
Yeah, Kartika.
Kartika, yes, sir.
So are you ready to present it?
Yes, sir.
Your co-host and then. Yeah, so please share your presentation.
Hello, sir.
Yeah, please share your presentation.
Well, PPT and start.
1 sec, sir.
Okay.
Yes, ma'am. Kartika, please share your screen.
Once, ma'am.
Share your screen, ma'am.
1 sec, ma'am. Are you visible, ma'am?
Your presentation is not visible. Please share it.
Hello, sir. I just the screen.
Not visible, no? Once again, unshare and yeah.
Share, yeah, now it's, yeah.
Okay, okay. Are you visible, sir?
Yeah, now it's visible.
Sir, share the screen.
Yes, yes.
Hello?
Before starting, can you put it in the share,
Oh,
rotate your
share the
screen.
screen.
You rotate your screen so that it is visible in the larger view. Rotate the screen of your phone directly. Yeah.
I mean, good evening to everyone. My project title is LDPs based polar decoding using belief propagating. I'm S. Karthika and I'm from engineering college. The objective of my project is polar code using LDPs based method using belief propagation. So the literature survey. The first one is channel polarization, constructing capacity achieving code for symmetric input discrete mammal channel. The inference is there was input to discrete memory channel via to the channel and the second one is hardware implementation for successive decoding of polar codes. Successive cancellation decoding implementation is reduce the complexity of multiplication and division operations and also reduces the of the each processing ends. And then low latency successive cancellation polar decoder architectures 2-bit decoding. In this compare with cancellation algorithm, in this 2-bit decode 2 bits simultaneously at the decoder side. Advanced advantages of 2-bit decoding and the latency is less than 25%. And the low complexity belief propagation polar decoder. This proposed scheme has also no performance loss and achieve reduction. And the one of the drawback is in this paper was is in nature, so the required latency energy dissipation is increased linearly. And then low latency successive cancellation list decoders for polar course multi-bit decision. It is reduces the latency of AC decoders. And then LDPC codes. LDPC is a low density parity check code. Is a linear error correcting code and is a Panner graph capacity approaching code. This decoder belief propagation used in applications requiring highly efficient information transfer. And the polar course channel capacity recently adapted to 5G standard. Code 1024 is used in 5G. Up to only use n is equal to 10. Polar course are the channel capacity for infinite length course. For poor infinite length has a poor performance. Successive cancellation list and successive cancellation is not suitable for in this method. So we write the project in belief propagation. Successive cancellation decoding achieve channel capacity infinite length course reduces complexity of each processing element. Put and low area implementation. Hardware complexity is what is the architecture of the pipeline tree SA architecture. The code length is n is equal to 8. The number of tree stages. Their first stage is the bit is a P 4 PS available. So 2 information bits are passed to P. Then we combine with 1 bit and then so on. This is the time requirement. The number of clock cycles required n is equal to 8. This is the simulated output. In this project, we done output for n is equal to 8 and 16, and then 2-bit. 2-bit is a reformulation of stage in the AC decoding. So we decode at the recorder side 2-bit. So it is the advanced advantages of 2-bit decoding. Reduce latency performance loss. This is the architecture of the 2-bit decoder architecture. And this is the clock cycle of the number of, it is a merged in architecture F unit, G unit. So we merge the F and G unit. So we reduce the number of 7. In the previous AC decoding, the number of clock cycle we can see 14, but the 2-bit decoding is so clock cycle is reduced means time requirement is we done simulation output for n is equal to 16. The main drawbacks is long decoding latency, not suitable for iterative decoding and deduction. So we BP decoding. It's the graphical representation is H matrix, check nodes and bit nodes. We easily consider with check nodes and bit nodes, we will get the matrix. So polar curves are the more attractive for capacity matching performance, encoding and decoding complexity. So polar curves are successive cancellation decoding and bleed propagation. Decoding is a channel capacity for infinite length polar curves and low, but AC decoding is not suitable for finite length because rate. That means it is a serial decoding. But BP is the parallel decoding nature. So we go to BP is a low. It is suitable for the low latency applications. The information bits are decoded one time in SCD, but not like that. So in this project, we use a mat Verilog and Verilog simulation to get the. This is the reliability sequence. N is equal to 8, 16, 30. From this, we get from N is equal to 1024. From this reliability sequence, easily get the N is equal to 8, 16, and 32, etc. N is equal to 2n stages are there. N minus positions are there. K bits as message bits and n minus k is the frozen bit. Frozen bit means represent as 0. Bits as represent as 1. Code word is equal to x is equal to u means parity bits and g is equal to generator matrix. The generator construction is based on the formula. It's a polar encoder. So frozen bits are represented as 0. Data represented as 1. BP decoder factor graph. Here the red color frozen and the block is represented as check nodes and green color are represented as the outputs and remaining check nodes. The black represent as the information. Dense factor graph. In this graph, we with which lines connected to other check nodes. That one connected to the dense factor graph. So the number of matrix size will be reduced. So pruning algorithm main for the BP decoding. So pruning algorithm is a very important one. It simplifies the H matrix size and the latency also. Pruning is a pruning algorithm. Here combined is a LCH equal to 0 means we remove the check node from the graph, available the variable node. Then in this we always variable node pass the 0 to the we remove the check node in this graph. Degree to variable check node means two check nodes, remove the variable node. Here two variable node, remove check node. This is the black diagram of our project. Encoder BPSK modulation. First information bits are then BPSK modulation we applied. Then only we decode the bits. This is the formula. It's a check node processor. The first we use comparator. Comparator means some is approximation is obtained. Then only we compare the sign bit and magnitude bit. Variable node processor. Variable node processor means alpha is message from check node. Beta means message from variable node to check node. This is black diagram is a message processing algorithm. First we get processing, then the beta value is first get, then only we processing alpha value we will be get. The simulator output for check node and variable node. This is the flow chart of my project. HMAC and log like LLR value and encoded code word. These all get from MATLAB. We return the code in MATLAB from the MATLAB. So then only relog generation also get from the mat code is easy to return the code in mat. We transfer into the .v file generation. Then we get so LLR values is output is given as in the Verilog generation. Then only we compare the estimated output. If equal means iteration stop, other iteration will be continued. The LLR value is the input, output is similar. If equal means the iteration stop, the otherwise iteration will be. This is simulation output for 8,4 polar code. So we get output once, then only we stop the simulation. This is the simulation output for 16,8. This is design. So design summary, we in this project we done 64, 256, 512 also. So number of LUT used only we mentioned here. So, and the conclusion of the project is this method, decoding method gives performance compared to SC2B decoding method. Believe from parallel decoding nature, the size of the matrix is reduced and results in complexity area and the power consumption when with successive cancellation decoding and 2-bit decoding. Also messages in a less number of clock cycles. Is the reference? Thank you.
Thank you.
Sir. Sir.
Yeah, just wait.
Ma'am, go to the table. Please go to the table. The result.
1 sec, ma'am.
What is the first column, ma'am? First column. You have written design summary. I think it's not.
Yes, ma'am.
What is that? What is that column?
It is the number of colons we used.
Number of?
Which colons we used for simulation. N is equal 8, 16, 64, 256. 2 we used the code length. So we now written as the design summary.
Then why the registers available are same from 8 to 256?
Not here, ma'am.
See, from 8 to 256, the registers available are same you are mentioning.
In this we use the same then only yes, ma'am. What, ma'am?
Hello.
Yes, ma'am.
No. You have increased from 8 to 256 here. Then why the registers available are same?
Ma'am, we done with the same kit is zinc we use in this processor. Same the memory is same.
No, it's not advisable, no?
Let me tell. I designed 8 to 256 in the same process. I mean same kit.
No, ma'am. Here this is device utilization, right? Device utilization. You might have used the same kit, but device utilization should be different from 8 to 256, correct?
Yes, ma'am. Device used is plate column. This is LUT available means I mentioned the number of LUTs and number of registers in that kit.
This is device utilization, correct?
Device yes, ma'am. This is a LUTs used and LUTs registers used. Those two columns are device utilization.
Okay.
So that means for the 512 old length, we have used a different.
Sir, not audible, sir.
The fifth one, which is 512,
512.
you have used a different kit, is it?
Yes, sir. You use a different kit.
Okay. Thank you.
No. Okay, ma'am.
I think there's some.
Thank you, sir. Thank you, ma'am.
I think P11 is not available, sir.
Yes, ma'am. P11 is not there, and P08 is having connectivity issues.
Yes, yes, yes.
Should we?
I think, please wait for just 5 minutes, sir. For any, they may join like this. 5 minutes. After that, you can end up the meeting, sir.
So please wait for 5 more minutes. Let's wait if others can join in. Is anyone present from the first paper, P001? Karthikeyan, Parvati, or Priyadarshini? don't think it's coming. So let's thank everyone. Thank you all the presenters and all the attendees who were there. Thank you for attending. Thank you for coming and thank you for attending the conference. The conference will go on tomorrow. It will start at 10 a.m. And the keynote will start at 10 a.m. And share you the schedule for tomorrow. So tomorrow you have, it will start at 10 a.m. and there will be keynote speakers. The first one is Dr. Prabha Sundaravardel. She is an assistant professor at Department of Electrical Engineering, UT Tyler. Then we'll have a keynote from a person from Xilinx India, Mr. PVV Ranganath. Then after lunch, the final keynote will be Mr. K.S. Ramanujan, who is who is the CEO and MD in many companies, and he will talk about electrical vehicles and the challenges of the same. And from 3 p.m. onwards, we'll again have some technical presentations from other presenters who are there. So please try to attend these presentations. Try to come on 10 a.m. Thank you again for attending. Keep on giving your feedback on how did you like the presentation and how was the conference organized. Please feel free to give your feedbacks so that we can improve on it in the future. Thank you, everyone. We can end the session here now. So, yes. Yes, sir, I made you the host. Please unmute.
Saurabh, yeah.
Yes.
Thank you so much, Sridevi ma'am, Saurabh Nagar, and Prateep. You have done a wonderful job. So I think Professor Saurabh has briefed what will be the agenda tomorrow. So please try to attend all the sessions. Thank you from our end. We will meet tomorrow. Saurabh, bye. Thank you.
Bye. Thank you, sir.
Madam is there?
Sorry, sir? No, ma'am. She has a class. So she has
okay, fine. Thank you, Saurabh. Thank you. Thank you. Bye. Thank you, participants. We will meet tomorrow. Thank you.